Welcome, dear listener, to a tranquil contemplative descent into the deepest, most ancient currents of geological time. Tonight, as the gentle quiet of the evening settles around you, and the distant sounds of the modern world begin to recede, fading into the peaceful, comforting background, we invite you to allow your imagination to slowly unfurl, like an ancient fern frond reaching for the subtle light of a primeval sun. Let it transport you far, far back through unimaginable stretches of time, reaching across hundreds of millions of years, past the brief age of humans, past the long age of mammals, to a world scarcely recognizable, yet fundamentally the same planet we inhabit. This is a journey not of haste, not of hurried discovery, but of profound tranquility, of slow unfolding, and of gradual serene discovery, allowing each detail to settle gently into your mind. We will focus not yet on the magnificent A whisper of creatures motion disturbed the profound darkness. that so capture our The very collective ground beneath imagination, ancient those skies thunder lizards quivered, of legend, not the but wrath of rather a on the very deity, nor primordial the fury stage of a upon which tempest, they would but something eventually infinitely make their older, grand and indelible profoundly more entrance. alien. Imagine, For if you eons will, a before world humanity utterly ever distinct graced this from the planet, vibrant, colossal fragmented beings continents reigned, that shape with our jaws modern like geography, formidable the familiar bone-crushing patterns of instruments, land and and eyes sea. that seemed to Picture gaze a through the single very colossal fabric of time landmass, itself. a Dinosaurs were supercontinent not of merely truly creatures of flesh and blood. scale, They were
an unbroken
embodiments of
immense
primeval
expanse that
legend,
majestically
sculpted by
dominated
the
the
relentless
entire planet.
forces of
This
evolution,
was Pangaea,
and ultimately
a
crowned by the
continental
grand
behemoth
tapestry
that
of
for vast
chaos.
epochs,
Then, in the
spanning
mere
from the
blink
late
of a cosmic
Paleozoic
eye,
through much
their
of the
epoch
Mesozoic,
ended. Now
united
it is their
nearly all of
hardened
Earth's
remains, their
terrestrial
fossils,
crust.
that
It was a
gently unveil
singular,
their
immense
deepest
landmass,
secrets.
a
Scientists
geological
delve into
masterpiece
layers of
bathed in
stone and
ancient
utter
sunlight,
silence,
its
slowly
continuous
bringing to
shores
light
kissed by a
immense
single
claws,
global
longer
ocean
than
known
many
as
swords,
Panthalassa,
and
or
incredible
the
beings
All-Sea,
adorned
a
not
vast,
with
boundless
scales,
expanse
but
of
with
water.
intricate feathers.
Pangaea
Once
stretched its
envisioned
immense
as
form
sluggish,
from one
cumbersome
pole to the
beasts,
other,
they
a
are now
gargantuan
understood as
silent
agile,
leviathan
intricate,
sleeping peacefully
and possessing
on
a
the face of the
terrifyingly
planet,
keen
its sheer
intellect.
presence
The
reshaping
Earth,
the very
for an
dynamics
astonishing
of the
stretch
Earth.
of over
Its monolithic
160
existence,
million
its
years,
sheer
was the
unbroken
undisputed
size,
domain of
profoundly and
dinosaurs,
intrinsically
a
shaped
truly
the global
diverse
climate,
assembly of
creating
reptiles.
unique atmospheric
These
and
captivating
oceanic
beings
circulation
first
patterns.
emerged during the
It sculpted
Triassic
the immense
period,
ocean currents that
approximately
circled its
230
vast shores,
million years ago,
dictating the distribution
and
of
maintained
heat
their
and
planetary
nutrients,
supremacy
and ultimately,
until their
irrevocably,
dramatic vanishing
dictated
act
the very
at the
course
close of the
life for
Cretaceous
hundreds of
period,
millions of years,
around
setting
66
the
million
fundamental
years ago.
environmental
Their
parameters
legacy
for
is
all that
etched
would follow,
deeply into the very
including the great
strata of our
radiation of
world's
reptilian
history.
forms.
To
The
classify
very
a
heart
creature
of this
definitively as a
supercontinent was so
dinosaur,
far removed from
scientists
oceanic
rely on
influence
several
that its
distinct
climate
anatomical
behaved in ways
markers.
almost alien to
Foremost
our
among
current
these are their
experience,
erect
giving
limbs,
rise to
positioned
unique
directly
challenges and
beneath the body,
opportunities for the
a departure
burgeoning
from the
life within its
splayed-out
vast
stance
interior.
common to
The
most other
geological
reptiles.
forces that assembled
This structural
Pangaea were
advantage
immense,
permitted highly
folding
efficient
ancient mountain
locomotion,
ranges that
and was
crisscrossed its
crucial in
surface,
supporting their
further
often
influencing
enormous
wind
bulk.
and weather patterns.
Furthermore,
In the
dinosaurs
early chapters
exhibited
of the
characteristic
Mesozoic
hip
era,
bone
specifically
configurations,
during the Triassic
falling into
period,
either a
the
lizard-like
epoch
or
when
bird-like
dinosaurs first
arrangement.
began their
A crucial
humble,
identifying
almost
feature
imperceptible
within their
emergence
skulls
from
was the
smaller
antorbital
reptilian
fenestra,
ancestors.
a unique
Pangaea
opening
remained a
situated
unified,
between the eye
coherent
socket and
entity.
nostril,
This
absent
singular
in other
continental
reptilian groups.
configuration, without the
Finally,
moderating
many
and
dinosaurs possessed
moisture-distributing influence
pneumatized
of numerous
bones,
scattered
bones that were
oceans
remarkably
and countless
hollow,
smaller
a
land
trait
masses,
shared with their
meant that the
closest
vast
living relatives,
interior of this
modern
immense
birds.
continent was
It's
subjected
essential to
incredibly
clarify that
extreme
not
and
every
often
prehistoric
volatile
reptile
climates.
was a dinosaur.
Far from the
Magnificent
tempering touch of
flyers
the
like
great bodies of
pterosaurs and
water,
formidable
which
marine
today absorb
inhabitants
and
such as
release heat to
plesiosaurs,
moderate temperature
while sharing the
swings,
Mesozoic
these sprawling
stage,
inland
represent
regions
separate
experienced
evolutionary
relentlessly
branches. The
scorching
term
arid summers,
dinosaur
where
specifically
temperatures
denotes
could
those
soar to
terrestrial
unimaginable
reptiles
baking
bearing
heights,
this unique collection
creating
of
landscapes
features,
of sun-baked
underscoring
rock,
the
cracked
incredible
earth, and
biological
shimmering heat
variety of
haze
ancient
that
Earth.
stretched to the horizon,
The initial
obscuring
emergence
the
of
distant
dinosaurs on
mountains,
our planet
and,
unfolded
conversely,
during the
they
Triassic
endured bitterly
period,
cold, bone-dry
approximately
winters, often
230
swept by
million
fierce,
years ago.
desiccating winds that
This
scoured the
particular
land,
epoch
carrying
marked a
away loose
truly
sediment
profound
and freezing
turning
any
point in
exposed
the Earth's
surfaces,
unfolding
plunging
narrative.
temperatures
As
below
the colossal
freezing, even near the
supercontinent,
equator.
Pangaea
Geological
commenced
evidence,
its slow,
meticulously
inexorable
gathered from
process of
ancient rock
fracturing.
formations found
This
in
continental
regions that were once deep
rearrangement
within Pangaea,
gave rise to
combined with
entirely new
invaluable insights
geographical
gleaned from
configurations
fossilized plant
and,
life and ancient soil
consequently,
structures,
fresh
paleosols,
ecosystems. The
strongly
very
suggest
first
that immense
dinosaurs to
deserts
grace
and
this
expansive
evolving
semi-arid
landscape
zones
were
dominated
far
much
from
of
the
Pangaea's
gigantic,
interior.
iconic
These
figures we
arid
often
belts stretched
envision.
for thousands
Instead,
upon thousands
they were
of miles in
typically
every
small,
direction,
remarkably
forming an
agile
unforgiving,
creatures.
desolate
These
landscape
early
of vast,
pioneers
shifting
of the
sand
dinosaur
seas,
lineage
towering
shared
dunes
their
shaped by
nascent
ceaseless
world with an
winds,
array of
and
other
stark eroded
reptilian
rock
forms,
outcrops that stood
the
like
embryonic
ancient
beginnings remains of mammalian life
attempting to persist
and a
in these
varied
harsh,
tapestry
challenging
of ancient
conditions was
flora.
exceptionally
Over the
tenacious
course of
and
countless
remarkably
millennia,
specialized.
These
comprised of
foundational
drought-resistant
dinosaurs
plants
underwent
that
a
clung
process of
precariously to
profound
existence in
diversification.
sparse oases,
They
or
adapted
along
with
ephemeral
remarkable
streamlets that
efficacy,
flowed only during
slotting
rare
into
rainfall.
and dominating a
Resilient,
multitude of
early
ecological
reptiles had
roles.
developed
Their
specific
ascent to
physiological
global
and
supremacy
behavioral adaptations
wasn't an
to survive the
instantaneous
brutal
event.
extremes,
It was a
such as
gradual
deep burrowing to
incremental
escape the
process
most
spanning
intense
millions of
temperature
years before they
fluctuations,
truly
or entering
became the
periods
Earth's
of
most
dormancy,
dominant
a form
terrestrial
of ancient
fauna.
estivation,
This
to
remarkable
conserve
rise
precious
was in
water
part
during
attributable
prolonged
to their
droughts.
inherent
Along the vast
capacity for
undulating
adapting to
coastlines
shifting
of Pangaea,
environmental
however,
conditions,
where the immense
and their
currents of the
impressive ability
Pan-Atlantic
to
Ocean brought
outcompete
forth
other
a generous
coexisting
life-giving
reptilian
moisture,
groups.
the climate
The
was
arrival of
notably more
dinosaurs set
monsoonal.
the stage
This
for
meant
one
it
of the
was
most
characterized
compelling
by
and
strong,
enduring
predictable
chapters in our
seasonal
planet's
rains that
biological
alternated with
heritage.
distinct
Their
prolonged
initial
dry
appearance,
periods.
followed by their
These seasonal
extensive and
deluges would
successful
transform
evolution,
landscapes,
would
causing
profoundly
ancient
shape
rivers to
Earth's
swell and
ecosystems
creating
for over
vast but often
160
temporary
million
wetlands
years,
that teemed with
leaving an
life during the
indelible
wet
impression on
seasons,
our world
only
that
for
we
the sun to
continue,
eventually
with
bake
great
them dry
dedication,
again,
to
leaving
meticulously
behind cracked
excavate
mud.
and explore to
These
this
coastal
very
belts,
day.
while still posing
The Earth
significant
witnessed the
environmental
undisputed
challenges with
reign
their
of
seasonal
dinosaurs
deluges
for
and
an
droughts,
incredibly
were undeniably
protracted
far more
duration,
hospitable,
encompassing
fostering lush,
approximately
albeit primitive vegetation.
165
They
million
served as
years.
vital
This
biological
immense
cradles, providing
geological
a fertile
expanse,
ground for much of the
formerly
evolving
recognized
terrestrial
as the
life,
Mesozoic
including the
era,
very first
is neatly
tentative stirrings of
segmented
the
into
dinosaur
three
lineage,
distinct and
a faint
significant
whisper of the
time
colossal
frames:
giants
the
that were yet to fully
Triassic,
unfurl
the
their immense
Jurassic,
forms
and the
upon this ancient
Cretaceous.
earth.
Their
The dramatic
planetary
contrast
dominance
between the
commenced
parched,
around
unforgiving
235
heartland,
million
the
years
seasonally
ago
drenched,
during the Triassic,
life-sustaining coasts
the
painted
period
a
when the
vivid, compelling
pioneering
picture of early
dinosaurian
Mesozoic
forms
Pangaea,
first
a
branched
world
off
of
from
stark
earlier
geographical and
reptilian
climatic
ancestors.
divisions that shaped
Throughout
life's
their
possibilities.
extensive dominion,
The
these
very
creatures
atmosphere of the
diversified
early
into an
Mesozoic,
astonishing array of
particularly during the
species,
Triassic
from the
and early
colossal
Jurassic,
sauropods,
was also
whose very steps
fundamentally
resonated
distinct
through the
from
ancient
air we
ground,
breathe in our
to the
modern
nimble
era,
feathered
its unique
theropods,
composition
whose
playing
lineage
an
would
absolutely
surprisingly
crucial
culminate in the
pervasive
birds we
role in
observe
shaping the
today.
prevailing
They displayed an
environmental
unparalleled
conditions across the
adaptability,
supercontinent.
thriving in
While
diverse
oxygen
habitats
levels
ranging
underwent
from dense
gradual
verdant
fluctuations
tropical
throughout the
forests
Triassic
to
and
stark
into the
parched
Jurassic,
deserts, and even
generally
remarkably
remaining robust
enduring the
enough to
conditions
support
of
large
polar
animal
regions.
life.
The abrupt
concentration
cessation of their
carbon
rule
dioxide,
occurred approximately
CO2, was
66
markedly
million
and
years ago,
consistently elevated
coinciding with the
compared to
conclusion of the
present-day levels.
Cretaceous period,
This abundance
a
of carbon
cataclysmic
dioxide
global
acted
event,
as a powerful
strongly
greenhouse
implicated as a
gas,
massive
far
asteroid
more
impact,
potent in its
triggered a
heat-trapping
widespread
capabilities
extinction
than
event.
today's
This
concentrations,
catastrophic phenomenon
efficiently
led to the
retaining
demise of
immense
roughly
quantities of thermal
75%
energy
of all
within the
plant and
atmosphere.
animal species
This
on
thereby
Earth,
contributed
including the vast
significantly to a
majority of
generally
non-avian
warmer global
dinosaurs.
climate,
This singular
creating
event
conditions that were
definitively marked the
universally
end
more
of the
tropical
Mesozoic
or
era,
subtropical,
simultaneously
extending
clearing the
towards the
ecological
poles.
stage for the
This
subsequent
sustained
proliferation of
warmth,
mammals.
unmitigated by
To truly
significant
grasp
ice
the
masses
monumental
or
scale
vast
of the
polar
dinosaurs'
glaciers,
enduring
prevented the
supremacy,
formation of
consider
any
this:
large permanent
modern
ice
humans,
caps at the
our own
poles,
species,
even
have
during
existed for a
periods
mere
of relative global
300,000
cooling,
years, a
meaning
fleeting
that even
instant when
polar
compared to
regions
the
might have
vast
seen
chronological
forests
sweep
rather
of the
than ice.
dinosaurs' time
The
on
ancient
Earth.
sky
Their
itself
prolonged
might have
sovereignty
presented a
allowed for
subtly different
unparalleled
visual
evolutionary
character to an
diversification
observer.
and the
It could have
development of
appeared
incredibly
somewhat
intricate
hazier or
ecosystems,
thicker,
elements that
perhaps even
continue
with a
to
slightly
captivate
different
scientific
muted
inquiry
tint,
and ignite our
subtly
collective
altered by the unique
imagination.
atmospheric
The
composition
Mesozoic
and
era,
the occasional
often
presence of
majestically
fine
dubbed
volcanic
the Age
dust
of
or aerosols
Reptiles,
from
is
ongoing
chronologically
geological activity,
segmented into
which would have
three
diffused
distinct and
sunlight in unique
consequential
ways.
periods,
This warmer,
each bearing
often
its
more
own
humid
unique
atmosphere,
ecological
particularly
signature.
in the
The
coastal
first of
belts,
these, the
enriched with
Triassic
elevated
period,
CO2,
commenced
directly
around
stimulated and
252
supported the
million
prolific
years
growth
ago.
and widespread
This epoch
proliferation
marked a
of vast
critical
forests
phase of
composed
global
ancient
recovery,
towering plant
following the
types.
devastating
These lush
Permian
botanical
extinction,
communities,
a
primarily
biological
conifers,
cataclysm that
cycads
had
and
drastically
ferns,
reshaped
provided
life
the
on
necessary
Earth.
biomass,
It was
the
within
very
this recovering
fundamental energy
world that
source
the
for
very
later
first
dramatic
dinosaurs
emergence
tentatively
and subsequent
emerged,
immense growth of
alongside the
immense
primitive
herbivorous
progenitors
dinosaurs.
of mammals.
The very air
Following
they
the
would one day breathe,
Triassic, in
the
geological
atmospheric pressure and
succession,
composition,
was the Jurassic
and the pervasive
period,
warmth
which
that
began
enveloped their
approximately
world,
200
were intricate
million
products
years
of
ago.
vast,
This
slow
era is
geological and
particularly
atmospheric
renowned for
forces,
witnessing the
elements far
undeniable
grander and
supremacy
more
of the
ancient than
truly
any
immense
single creature.
dinosaurs,
This
the
deep
very
systemic
titans that
interaction
frequently
between
dominate our
geology,
popular
atmosphere, and
imagination.
biology
It also saw
laid
the
the essential,
remarkable
profound
evolutionary leap
foundation
of
for
the
the age
first
of
migratory birds. The global environment during the Jurassic was characterized by expansive, verdant vegetation and a consistently warm, often humid climate, crafting an ideal setting for the proliferation of these ancient giants. The final segment of the Mesozoic era was the Cretaceous period, commencing around 145 million years ago. During this significant time frame, a pivotal biological innovation occurred. Flowering plants, or angiosperms, made their grand debut and rapidly diversified, profoundly altering the terrestrial plant landscape. The Cretaceous, however, concluded with a cataclysmic flourish approximately 66 million years ago, marked by a mass extinction event that tragically eradicated the non-avian dinosaurs and a vast multitude of other species. Each of these periods, from the initial Triassic to the culminating Cretaceous, introduced profound ecological shifts, fundamentally shaping the trajectory of life as we understand it today. The Mesozoic era, as a complete geological span, endured for roughly 126 million years, serving as the silent witness to the magnificent rise and the dramatic ultimate decline of some of Earth's most iconic and awe-inspiring creatures. To establish the precise timeline of dinosaur fossils, scientists employ a suite of sophisticated and highly effective methodologies. A cornerstone technique is radiometric dating, which precisely quantifies the gradual decay of radioactive isotopes embedded within the rock layers, encasing the fossils. Specifically, potassium-argon dating proves exceptionally valuable for dinosaur remains, capable of accurately dating samples that are billions of years old. This method hinges on the consistent rate at which potassium-40 transforms into argon-40, providing a reliable geological clock for these ancient specimens. Another indispensable approach is biostratigraphy, wherein researchers meticulously analyze the sequential rock layers where fossils are unearthed. By studying the distinct assemblages of fossil species within these layers, scientists can establish relative ages and construct a chronological framework of prehistoric life. This technique often complements radiometric dating, yielding a more comprehensive understanding of a dinosaur's existence. Furthermore, magnetostratigraphy offers an additional avenue for dating. This method investigates the subtle magnetic signatures preserved in rocks which record shifts in Earth's magnetic field polarity over known intervals throughout geological history. By matching these patterns to establish timelines of magnetic reversals, scientists can deduce the age of the fossil-bearing strata. For more recent fossil finds, carbon-14 dating can sometimes be applied to remnant organic material. However, its utility for most dinosaur fossils is limited, as it is effective only for specimens less than approximately 50,000 years old. The combined application of these diverse dating methodologies allows paleontologists to painstakingly assemble an increasingly precise and accurate timeline of dinosaur evolution and their eventual disappearance. Dinosaurs and pterosaurs, while both magnificent inhabitants of the Mesozoic era, were fundamentally distinct groups of reptiles, differing in both anatomy and lifestyle. Pterosaurs were the planet's pioneering flying vertebrates, having developed powered flight. Their remarkable wings were constructed from a membrane of skin, uniquely stretched across an elongated fourth finger and connecting to their body. This specialized wing structure unequivocally set them apart from both dinosaurs and modern birds. Pterosaurs also possessed hollow bones and a keeled breastbone, providing robust attachment points for their powerful flight muscles, adaptations that convergently evolved with birds, but arose independently. When on land, pterosaurs typically adopted a more upright stance, yet their legs originated from the sides of their bodies, making them less agile on terrestrial surfaces, but exceptionally adapted for aerial locomotion. In stark contrast, dinosaurs were predominantly terrestrial animals. Although a lineage of dinosaurs eventually gave rise to birds, the vast majority were ground-dwelling creatures. They exhibited a wide spectrum of body plans, from the immense long-necked sauropods to the swift bipedal theropods. Dinosaurs were characterized by a distinctive hip structure and an upright limb posture, facilitating efficient movement on land. Another key anatomical divergence was in their skull morphology. Pterosaurs generally had relatively larger brains for their body size, and often sported elaborate cranial crests. Dinosaur skulls varied immensely, but typically possessed smaller brain cavities. Despite these crucial differences, both groups achieved extraordinary evolutionary success, dominating their respective ecological niches for millions of years until their collective extinction at the close of the Cretaceous period. The very word dinosaur itself carries a fascinating historical resonance, originating in the mid-19th century. It was precisely in 1842 that the renowned English paleontologist Sir Richard Owen first coined this powerful term. Owen ingeniously crafted the word from two ancient Greek roots, Dinos, which profoundly signifies terrible or fearfully great, and Sauros, meaning lizard or reptile. Sir Owen formally introduced this new nomenclature during a significant lecture delivered at the British Association for the Advancement of Science. His intention was to accurately categorize the fossils of massive extinct reptiles that had been recently unearthed in England. These ancient creatures were demonstrably unlike any living animals of the time, and Owen, with his discerning scientific eye, recognized them as a unique and distinct group of reptiles that had, in a bygone era, held absolute dominion over the Earth for immense stretches of time. The term dinosaur rapidly gained traction, not only within the burgeoning scientific community, but also, notably, resonated deeply within popular culture. It provided a succinct, yet immensely evocative label for these ancient marvels that were so vividly capturing the public's imagination. It's noteworthy that when Owen first employed the term, he was referring to only three specific genera: the powerful Megalosaurus, the herbivorous Iguanodon, and the armored Hylaeosaurus. Today, our collective scientific understanding has expanded exponentially, and we now identify hundreds of distinct dinosaur genera, showcasing an astonishing diversity of forms, sizes and lifestyles. While our comprehension of dinosaurs has progressed dramatically since Owen's initial conceptualization, his foundational term has remarkably endured. It continues, even now, to powerfully evoke images of those awe-inspiring beings that so grandly ruled our planet for over 160 million years, irrevocably shaping the trajectory of evolution and perpetually captivating our collective human imagination. The unraveling of the first scientifically documented dinosaur fossil is a compelling narrative from the dawn of paleontology in the early 19th century. Although large, unusual bones had been sporadically discovered and pondered for centuries, it wasn't until 1815 that the first such find was formally and scientifically described. This landmark achievement is credited to William Buckland, a pioneering English paleontologist and geologist. Buckland meticulously studied a lower jaw and other bone fragments unearthed from a quarry near Oxford, England. He subsequently christened the creature Megalosaurus, meaning great lizard, and detailed his findings in a seminal scientific publication in 1824. This event truly marked the inception of formal dinosaur paleontology. However, it's a crucial historical nuance that Buckland did not in fact coin the term dinosaur. That particular distinction, as previously noted, belongs to Sir Richard Owen, who introduced the word in 1842. Owen, with his broader comparative anatomical perspective, recognized that Megalosaurus and other recently uncovered large reptile fossils represented a coherent and distinct group of animals, which he then formally named Dinosauria. The fascinating saga of dinosaur discovery, of course, continued to unfold. Throughout the remainder of the 19th century, a steady stream of new fossils came to light, fueling a vibrant boom in the burgeoning field of paleontology. This initial era of discovery laid the essential foundation for our comprehensive modern understanding of these compelling prehistoric creatures that once held sway over our planet. Despite the continuous flow of groundbreaking scientific discoveries in recent years, many people still harbor outdated or, regrettably, inaccurate notions regarding dinosaurs. A particularly common and enduring misconception is the belief that all dinosaurs shared a single synchronized lifespan, emerging and perishing in unison. In reality, the dinosaurian lineage spanned an immense 160 million years, a vast temporal canvas upon which diverse species continually evolved, flourished, and in time went extinct. It was a dynamic, ever-changing saga, not a static tableau. Another frequent error is the widespread assumption that every dinosaur was, without exception, a creature of colossal proportions. While some species, such as the magnificent Argentinosaurus, were indeed of staggering size, it's a fascinating counterpoint that numerous dinosaurs were no larger than, or even smaller than, contemporary chickens. Consider the Compsognathus, for instance, whose dimensions were roughly comparable to a turkey. Furthermore, a prevalent yet incorrect belief posits that dinosaurs were universally cold-blooded and sluggish, akin to modern reptiles. However, the preponderance of current scientific evidence strongly indicates that many dinosaur species possessed warm-blooded metabolisms and were remarkably active, with some quite capable of attaining impressive speeds. The imagery of lumbering, slow-witted brutes is largely a relic of older, less informed interpretations. Lastly, the notion that dinosaurs represent some form of evolutionary failure is far from the truth. These creatures commanded the terrestrial ecosystems for millions upon millions of years, and their direct descendants, birds, continue to thrive and diversify in the present day. Indeed, the sheer biological diversity and profound adaptability of dinosaurs stands as a powerful testament to their extraordinary evolutionary success. Through relentless dedication and cutting-edge research, Scientists have
crushing armored prey
meticulously
or larger
identified
fish,
and
acting as
formally named
powerful
over
ambush
1,000
predators.
distinct
These early
species
marine
of dinosaurs
reptiles
to date.
expertly
However,
exploited
this
different
impressive
ecological
tally is by
niches
no
within the
means
burgeoning
static.
marine
It
environments.
is a number that
Some
steadily
relentlessly
increases as
pursued prey in the vast
paleontologists
open water,
worldwide continue
relying
to
on
unearth
sustained speed
exciting
and
new
pursuit,
fossil evidence.
while others perhaps
It's
preferred
crucial
to
to
ambush
acknowledge that these
unsuspecting
currently
victims from rocky
catalogued
outcrops
species
or
likely
nascent coral
represent
reefs,
only a
using
fraction of the
stealth and
total
explosive
number of
power,
dinosaur
showcasing
species that
diverse
actually
hunting
existed
strategies
during
and a
their
wide array
immense
of
reign
feeding
on Earth.
behaviors.
The
The
intricate
coastal
process
areas
of
and brackish
discovering,
waterways
then
were also home
subsequently
to early, more
classifying a
primitive
new
forms
dinosaur
of
species
crocodilians
is
and
both
ancient
protracted
turtles,
and inherently
resilient
complex.
creatures that survived
Researchers
the Permian
frequently
extinction
contend
and
with
began to
incomplete
diversify
fossil
into
records,
various aquatic
which can
and
make it
semi-aquatic
challenging to
forms.
definitively
Some of these
ascertain
would
whether
later
a fresh
embark on their own
discovery truly
evolutionary
constitutes a
journeys
novel
towards fully
species
aquatic
or
or
merely a
semi-aquatic
variation of an
lifestyles,
already
developing
recognized
specialized
dinosaur.
limbs and
As
body
technological
forms for life in
capabilities
water,
advance
such as
and
paddle-like
scientific
feet or
methodologies
flattened,
become ever
powerful
more
tails,
refined,
adapting
our
to
understanding of
estuarine and coastal
dinosaurian
environments.
diversity
These
continually
diverse and
evolves,
burgeoning marine
sometimes
ecosystems,
necessitating
while distinct and
reclassifications
separate
or,
from the
on
terrestrial
occasion, the
domain that the
amalgamation of
dinosaurs would
previously
eventually
separate
conquer,
species.
were nonetheless
It is
intricately linked
particularly
through
interesting
global
to note
climate
that the
patterns,
pace of
the
dinosaur
grand cycles of
discoveries
the
has
Earth
markedly
system, and
accelerated
shared
in recent
atmospheric
decades.
conditions,
This
forming a
increase can be
unified living
attributed to
planet, where the
improvements in
fates of
fossil
terrestrial
detection
and marine
techniques,
life were
the growing
intimately
global
interconnected.
community of
The
researchers
vastness and
dedicated to the
interconnectedness
field,
of the
and the
Pangaean
systematic
Ocean provided
exploration
an
of
immense
regions
dynamic
previously
laboratory for
unexamined.
evolution,
Some estimates
fostering a
even
parallel
suggest
world
that
of
a new
ancient
dinosaur
giants and
species
agile
is
hunters
formally
beneath
named
the undulating
approximately every
waves,
2
a
weeks,
testament
a
to
fact
life's
that
pervasive
vividly
and
underscores
adaptive
the
reach across
dynamic
all
and
environments,
ever-expanding
from
nature of
mountain peaks to the
paleontological
deepest
inquiry.
abysses.
While the current
climate
enumeration of
dynamics of
known
Pangaea
dinosaur
were
species
largely
is certainly
intrinsically
impressive,
dictated
it
by
is in
its immense
probability
size and
just
its
the initial
singular
glimpse.
unified
Many
configuration,
paleontologists hold the
utterly unlike
conviction
the
that the
broken-up
total number of
continents of
dinosaur
today, which
species that
create
ever roamed
varied
the
weather
Earth could
systems
plausibly
and numerous
extend into the
localized
tens of
climates.
thousands.
With
This
no
profound
vast
and
oceans
breathtaking
breaking up its
diversity
monolithic
powerfully
landmass,
emphasizes the
global air
remarkable success
circulation
and astonishing
patterns were
adaptability of
profoundly and
dinosaurs
fundamentally
throughout their
different from those
extraordinary
that
160
characterize our
million year
modern
global
world.
dominance of
The
terrestrial
absence of numerous
ecosystems.
continental
The very
boundaries and
first
towering
dinosaur
mountain ranges
species to
meant
achieve
global
formal
winds could blow
scientific
almost
recognition
unimpeded
was
across vast
Megalosaurus.
stretches,
This was a
creating
truly
persistent and
formidable,
powerful air
large
currents,
carnivorous
a strong,
theropod,
consistent
a
monsoonal
creature that
system
roamed
likely
the Earth
dominated
during the Middle
equatorial
Jurassic
regions,
period.
driven
An
by the
incredible
immense
expanse
thermal
of time,
contrast
approximately
between the superheated
167
continental
million
interior and the
years
cooler
ago.
surrounding
This
Pamphalassic
groundbreaking
Ocean.
discovery,
This
a
system
true
brought heavy,
milestone in the
predictable
nascent
seasonal
field of
rains to the
paleontology,
extensive coastal
unfolded
areas,
in the early years
fueling
of the
ancient
19th
sprawling
century,
river systems
brought
and
to light
creating
by the
vast
diligent
but often
work of British
temporary
geologist
wetlands that
William
teemed with
Buckland.
life during the
He
wet
meticulously
seasons,
described
only to
this
shrink
ancient beast,
dramatically during
based
the
on a
long,
collection
dry
of
periods,
fossilized
leaving
bones
behind
unearthed from a
cracked
quarry
mudflats.
situated near
In
the
stark
historic city of
contrast,
Oxford,
the deep
in England.
interior of the
The name
supercontinent
Buckland bestowed
experienced
upon it,
extreme continental
Megalosaurus,
climates,
translates powerfully
characterized
to
by
great
dramatic
lizard.
and often
At the
brutal
time of its
temperature
initial
swings between
description,
day and night,
the very
where
concept of a
temperatures could
dinosaur
plummet
as
or
a
soar
distinct
rapidly
group of
by
animals
dozens of
had not
degrees
yet been
Celsius,
conceived or
and
established.
profound
Thus,
variations between
Megalosaurus was
seasons,
first
with long,
perceived simply
parched,
as a
dry
gigantic
periods that led to
lizard-like
severe
creature.
desiccation.
The fragmented
Geological
fossils
evidence,
Buckland
including
carefully
widespread
studied,
aeolian
including a
wind-blown
robust lower
sandstones,
jaw teeming with
indicative of
formidable
ancient
teeth,
deserts
a
the
series
size
of
entire
sturdy
modern
vertebrae,
continents,
and substantial
vast salt
limb bones,
deposits,
provided
formed from
compelling hints
evaporated
of a
inland
truly
seas,
fearsome
strongly
predator.
suggests
Based
that
on
immense
these
sand dunes
tantalizing
were
remains,
prevalent across these vast
Megalosaurus was
interior
estimated
deserts,
to have reached an
indicating
impressive
prolonged
length of about
periods of
9
extreme
meters,
dryness and
roughly the
relentless
size
high
of a
winds,
large bus,
creating a
and to
truly
have weighed
inhospitable
approximately 1
heartland,
ton.
a
The
desolate,
formal
unforgiving
identification of
interior that few large
Megalosaurus stands
creatures
as
could
the very
penetrate.
genesis of
This
dinosaur
climatic uniformity,
paleontology.
or rather,
However, it would
predictability
take
of
several more
extremes across
decades
such an
before the
immense
overarching
landmass
term
meant that there
dinosaur
were
was
far
finally
fewer
coined
distinct
by Sir
climate
Richard
zones
Owen in
compared to the rich
1842,
mosaic of
a word
climatic
that would then
regions we
encompass
observe today.
Megalosaurus
With its
and all the
diverse
other
biomes and
awe-inspiring
localized
prehistoric
weather patterns,
reptiles
the
that
gradual
continued to be
breakup of
unearthed.
Pangaea
This
into
pivotal
separate
initial
continents,
discovery
a
fundamentally
monumental
paved the way
geological
for all
process that began
subsequent
in earnest during the
paleontological
Jurassic
research.
period and
It ignited a
accelerated through the
profound spark of
Cretaceous,
both
would
scientific and
fundamentally
public
and
interest in these
irrevocably alter
enigmatic,
global weather
ancient
patterns.
creatures.
As
as
new
more and more
oceans slowly
fossils were
formed
slowly
between the
painstakingly
diverging
brought out of the
landmasses,
earth
their
and
presence
subjected
would
to
introduce
rigorous study,
significantly
our
more
collective
moisture into the
understanding of
atmosphere,
dinosaurs
create
and their
more varied
profound place
temperature
within Earth's
gradients
vast
across
and
new
ancient history
coastlines,
began
and
to
ultimately
steadily
lead to
take
a
shape,
far greater
ultimately
diversity of
blossoming into the
localized
rich and
regional
complex field of
climates,
dinosaur
fostering
science
new
that
biomes
captivates
and
us today.
habitats for life to exploit.
Dinosaurs trace
This
their
immense
profound
geological
evolutionary
restructuring,
lineage back
a
to a
slow-motion
specific group of
continental dance
reptiles
spanning
known as
millions of years,
archosaurs,
would
a
in turn
branch that
drive
first
significant
emerged
and
over
widespread
200
shifts in
million
global
years ago
biodiversity,
during the tumultuous and
profoundly influencing the
transformative
evolution and the
Triassic
geographical
period. The
distribution of
earliest
not just
members of this
dinosaurs,
ancestral
but
group
literally all
were
life on
typically
Earth,
small,
from the smallest
incredibly
microbe
agile
to the largest
creatures,
plant,
often moving on
adapting to
two
a
legs
constantly
and
changing
possessing possessing uniquely
The
specialized
very air
ankle bones
dinosaurs
that
breathed,
clearly
the intricate
distinguish them from
global
other
water cycle,
reptiles of their
and the
time.
precise
As the
distribution of
Earth's
all life
climate
forms
and its
across the
various
planet
environments
were intimately
underwent
and
gradual
profoundly
yet
products of
significant
this singular
shift, these early
supercontinental embrace,
proto-dinosaurs
its
began a
formation and its
remarkable
eventual
process of
magnificent
adaptation.
unraveling, a
They
saga
slowly,
of immense
subtly,
geological
yet
power that laid the
fundamentally,
foundation
developed
for the age
new
of
anatomical
giants.
features,
As the
traits that
Triassic
would ultimately
period
come to
slowly
define the
unfolded,
entire dinosaur
marking
lineage for
Earth's
millions
quiet,
of years to
arduous
come.
recovery
One
from
of the
the
most
monumental
pivotal
Great
and
Dying,
distinguishing
a
evolutionary
subtle yet
advancements was the
profound stirring
repositioning of
began
their
to
legs.
manifest on the
Instead of
vast
sprawling out
unified
to the sides,
landmass
a
of
common
Pangaea,
posture for most
it was amidst
reptiles,
the
their
recovery,
limbs began to
often
shift
stark
directly beneath their
ecosystems,
bodies.
the
This seemingly
burgeoning
subtle
conifer
change
forests
proved
that formed
immensely
deep,
advantageous,
silent canopies,
allowing for
and
far
the
more
sprawling
efficient
fern
movement
prairies
and
that
providing
blanketed
superior
ancient
support for what
floodplains.
would eventually
The
become
very
their
first
truly immense
dinosaurs
body
made their
weights.
humble,
Over vast
tentative,
stretches
yet
of
historically
geological time,
monumental
different
appearance.
dinosaur
These
groups branched
pioneering
off,
creatures
each
were
evolving its own
remarkably
distinct
quite
and
different from
specialized
the colossal,
characteristics.
iconic figures
Some,
that
through
would
this
later
slow
dominate
dance of
the
natural
Jurassic and
selection,
Cretaceous
grew into
landscapes.
colossal plant
Those
eaters,
famous titans
adorned
of
with
popular
impossibly long
culture.
necks and
For a
sweeping
moment allow
tails.
your mind
Others
to gently
evolved into
set aside
fearsome,
the immense
highly
bulk of a
efficient predators,
Brachiosaurus,
armed with
whose
razor-sharp
neck could
teeth
reach
and
dizzying
immensely
heights,
powerful
or the
jaws.
terrifying
The evolution
grandeur
of dinosaurs was by
Tyrannosaurus
no
rex,
means a
whose
singular,
roar shook the
straightforward
very ground.
progression.
The
Instead,
earliest
it was a
dinosaurs
complex,
were, by
intricate
and
branching
large,
of countless
small,
species,
agile, and
unfolding
relatively
patiently over
unassuming
millions
beings,
upon millions
often
of years.
overshadowed and
Within this
outcompeted
grand
by other,
evolutionary tree,
more dominant
some groups,
reptile groups
notably
of
the
their time,
theropods,
yet
would
carrying
eventually
within
embark
their
on a
evolving
path that,
forms the
against
latent
all odds,
blueprint for
led directly to
unparalleled
the
future
existence of
success,
modern
a
birds.
genetic
This
promise of
incredible
global
evolutionary
supremacy.
journey profoundly
Consider, for
demonstrates
instance,
nature's
one of the
remarkable
earliest
and
known
seemingly
dinosaurs,
boundless
a
ability
creature
to
whose
generate a
very
vast
name
array of
whispers
diverse
ancient
life forms,
beginnings.
all stemming from a
Eoraptor
common shared
lumensis.
origin.
Its name
As these
beautifully
magnificent
translates to
dinosaurs
dawn
continued their
plunderer
slow,
from the Moon
relentless
Valley.
process of evolution and
Poetic nod to its
diversification,
incredibly
they
ancient
gradually,
origins,
yet
and the
undeniably,
fossil-rich
came to dominate
Ishigor
terrestrial
Alaska formation
ecosystems
in
across the
Argentina,
globe.
where its
For
remains
over
were first
160
discovered,
million
a place
years,
where the
they shaped the
landscape
very
itself
contours
seems
of the
to
ancient
echo with
world in ways that we
primordial
can still
history.
observe and
This
interpret
diminutive
through the
creature was a
invaluable whispers of the
graceful,
fossil
purely
record today.
bipedal carnivore,
Their story,
meaning
a
it
testament
walked
to evolutionary
exclusively on its
success,
two hind
offers
limbs,
profound
but
insights into
stood
the
perhaps
fundamental
only about
processes
3
of
feet long
adaptation
from the tip
and the
of its
branching
slender snout
speciation
to
that
the very
relentlessly
end of its
drive the
long
unfolding of
balancing
life on
tail,
Earth.
and might have
The
weighed
vast
no
and
more than a
astonishing world of
medium-sized
dinosaurs
domestic
is
dog, a
scientifically
mere 20
categorized
pounds.
into two
Its
primary
slender,
divisions,
athletic body,
a
combined with
classification
noticeably
system
long
rooted in
hind
the
limbs,
subtle yet
made it
significant
swift and
differences
nimble.
within their
Its
hip
skull
structures.
relatively large
These
for its
two
body,
major groups are
housed
known as the
small, sharp,
Saurashia
serrated
and the
teeth,
Ornithoschia.
perfectly
The
adapted for a
Saurashia,
diet of
a
small
term whose
lizards,
Greek roots
agile
translate
insects, and
intriguingly
perhaps
to
the
lizard
vulnerable
hip,
hatchlings of other
encompasses
reptiles
two
that nested
incredibly
in the
well-known and
undergrowth.
distinct
Eoraptor's
subgroups,
skeletal
the
structure was
theropods and the
incredibly
sauropods.
primitive, almost a living
Theropods, for the most
snapshot of
part,
early
were formidable
dinosaurian
carnivorous
evolution, a
dinosaurs,
mosaic of
characterized
features that
by their
offered
bipedal
tantalizing glimpses
locomotion,
into the
striding
characteristics of the
confidently
common
on two
ancestor of
powerful
all
legs.
dinosaurs.
Among
Its
their ranks were
five-fingered
some of the
hand,
most iconic
notably,
predators,
featured
like
one
the
digit
fearsome
slightly longer
Tyrannosaurus
and
rex.
more robust than the
Sauropods,
others,
on the other
hinting at a
hand, were
specialized
their gentle,
grasping
towering
ability, crucial
counterparts,
for deftly
herbivorous
catching agile
giants
prey
distinguished
amidst the
by their
dense
impossibly
Triassic
long
undergrowth.
necks and sweeping
Imagine
tails,
this small,
moving
quick hunter,
ponderously
a
on
shadow
four
among the
columnar
shadows,
legs. The
darting
magnificent
silently through thickets of
Brachiosaurus
tough
stands as a
fibrous cycads
quintessential
and sprawling
example of this
ferns.
group.
Its light,
The
almost
Ornithoschia,
imperceptible steps
conversely,
barely
are
disturbing
referred
the
to as the
ancient soil,
bird-hipped
a silent
dinosaurs.
harbinger of the
Intriguingly
truly
and
colossal
somewhat
age of giants
counterintuitively
that would
given the
one day
name,
follow its
all members of
evolutionary
this
path.
diverse group were
Another key
herbivores.
player,
This
the
division
slightly
includes
larger
universally
contemporary for this
recognizable
nascent
dinosaurs,
stage of
such as the
dinosaur
three-horned
evolution, was
Triceratops, the
Heregosaurus
plate-back
ishigor
Stegosaurus,
latensis,
and the
also
distinctive
discovered in the
duck-billed
same
hadrosaurs.
exceptionally rich
Ornithischians
Argentine
displayed a
formations,
remarkably broader
providing a
range of body
window into a
types
shared
and evolved a
ecosystem.
fascinating array of
Heregosaurus
defensive
was a
adaptations when
considerably more
compared to their
imposing predator
Saurashian
than
relatives.
Eoraptor,
Perhaps the most
reaching
captivating
impressive
twist
lengths
in
of
this
up to 20
evolutionary
feet,
tale is that,
about the size of a
despite the
modern-day
bird-hipped
saltwater
moniker,
crocodile,
it was actually
with
the
an
Saurashian
estimated weight of
theropods that
around
embarked on the
800
evolutionary
pounds,
path
while
leading directly
significantly
to modern
larger and
birds.
more robust.
This
It
surprising,
still retained
often
many primitive
counterintuitive,
characteristics
evolutionary
within its skeletal
trajectory powerfully
structure,
highlights the
making its
complex,
exact,
intricate,
precise
and frequently astonishing nature of dinosaur evolution and their profound, often unexpected relationship to the avian species that grace our skies today. Dinosaurs, after their initial appearance during the Triassic period approximately 230 million years ago, very quickly and efficiently adapted to fill a vast multitude of ecological niches. Their journey of diversification was a painstaking, gradual process, meticulously unfolding over many millions of years. This incredible evolutionary push was relentlessly driven by the relentless forces of environmental change and the ever-present pressures of natural selection. As the early Jurassic period dawned, dinosaurs began to assert their undeniable dominance across terrestrial ecosystems. This particular era witnessed the grand emergence of the long-necked sauropods, whose colossal forms would come to define the landscape, and the very first appearance of the theropods, the incredibly diverse group that would eventually lead to the evolution of birds, as the Earth's continents slowly shifted and drifted apart, giving rise to novel habitats. Dinosaurs continued their remarkable evolutionary dance. They evolved to skillfully exploit these new opportunities, developing an astonishing array of body sizes, adapting to a myriad of diets, and exhibiting a complex spectrum of behaviors. The Cretaceous period truly marked the zenith of dinosaur diversity. During this time, flowering plants made their dramatic debut and diversified with explosive rapidity, fundamentally reshaping plant communities and providing entirely new food sources and habitats. This profound botanical shift, in turn, fueled the evolution of highly specialized plant-eating dinosaurs, such as the magnificent hadrosaurs and the formidable ceratopsians. Concurrently, theropods continued to diversify, evolving into various predatory forms ranging from nimble, small, agile hunters to gargantuan carnivores like the iconic Tyrannosaurus rex. Throughout their incredibly long reign, dinosaurs continuously and dynamically adapted to constantly changing climates and the ceaseless pressures of competition. Some groups became more narrowly specialized, honing their traits for very specific niches, while others maintained more generalist characteristics, allowing them greater flexibility. This ceaseless process of diversification ultimately sculpted the incredibly rich and varied spectrum of dinosaur species that continue to captivate our imagination today, from the towering gentle Brachiosaurus to the swift agile and feathered dromaeosaurs. Among the truly vast and wondrous collection of dinosaur species that once graced our ancient Earth, some were of truly colossal proportions, creatures of such immense scale that they rank among the largest to ever walk the land. The Argentinosaurus, a monumental sauropod hailing from the ancient landscapes of South America, is frequently regarded as one of the most gargantuan terrestrial animals in the entirety of Earth's history. This enormous herbivore could stretch to an incredible length of up to 110 feet. Imagine more than 2.5 school buses placed end to end, and its estimated weight could reach as much as a staggering 80 tons. Its impossibly long neck was a biological marvel, allowing it to effortlessly browse on vegetation found high in the treetops, thus providing it access to food sources that were utterly beyond the reach of other, lesser herbivores. Another true giant was the Dreadnoughtus, whose evocative name translates to fears nothing. This titanosaur, also discovered amidst the fossil-rich grounds of Argentina, was nearly as massive as Argentinosaurus. Scientists have been incredibly fortunate to unearth remarkably complete fossils of Dreadnoughtus, which have provided an exceptionally clear and detailed picture of its immense size and intricate structure. The Patago titan, yet another colossal South American native, stands as a formidable rival to these behemoths in sheer scale. It is estimated to have attained lengths of up to 120 feet and weighed in the colossal range of approximately 70 tons. These impressive measurements are derived from several exceptionally well-preserved specimens, allowing paleontologists to make far more accurate and confident estimates of their true dimensions. While perhaps not possessing the extreme elongation of the sauropods, the Tyrannosaurus rex stood as one of the largest and most terrifying carnivorous dinosaurs known. It could grow to a formidable length of 40 feet and weigh up to 9 tons. This fearsome predator was, without question, the apex hunter of its era. Its powerful bone-crushing jaws and dagger-sharp teeth rendered it an utterly formidable carnivore, capable of pulverizing bone and tearing through the toughest hides of its dinosaurian prey. In fascinating contrast to the planet's gargantuan inhabitants, the diverse tapestry of dinosaurs that once roamed our ancient Earth also included creatures of surprisingly diminutive stature. Some were truly tiny compared to their enormous cousins. The smallest definitively known dinosaur, a swift and agile predator, was the Compsognathus. This tiny hunter lived during the late Jurassic period, approximately 150 million years ago. This minuscule dinosaur was, remarkably, roughly the size of a modern chicken, measuring a mere 60 centimeters in length, and weighing in at a delicate 3 kilograms. Another strong contender for the title of the smallest dinosaur is Anchiornis, a delicate feathered creature that once inhabited the region we now know as China, also during the late Jurassic period. Anchiornis was just slightly larger than Compsognathus, reaching
picture,
lengths
if
of
you
about
will,
30
a
to
world
40
still recovering
centimeters
from profound
and weighing a mere
catastrophe,
110
vast
grams.
and often stark,
Anchiornis
yet
holds
teeming with
particular
tenacious
significance
life.
due to its
The land
exceptionally
was still
well-preserved
united in the
fossils,
singular
which have provided
supercontinent of
scientists with
Pangaea, as
unprecedented
we
detailed
explored
information
earlier,
about
with
its
its
feather
immense
coloration,
interior deserts
offering a
of
rare
humid
glimpse into the
monsoonal
ancient
coastal
spectrum of
belts,
life.
creating
More
a stark
recently,
dichotomy of
paleontologists
habitats.
uncovered the
The
extraordinary
atmosphere has discussed
Oculudentavis
rich in carbon
congra,
dioxide
initially
and often
believed to be a
warmer,
miniature
fostered
dinosaur
widespread
perfectly
conifer
preserved within
forests,
ancient amber.
dense cycad
This creature was
groves,
astoundingly
and sprawling
small,
fern
with a skull
thickets,
measuring only
providing the
14
botanical
millimeters long.
architecture for the
However,
nascent
subsequent, more
ecosystems.
rigorous
While
research has
these
suggested that
landscapes were undeniably
Oculudentavis might
vast,
actually be a
they were
very
also
small lizard
subject to
rather than a
significant
dinosaur. A
environmental
nuanced
variability,
re-evaluation that highlights the
unpredictable
ongoing
seasonal
debates,
droughts that
continuous
withered
discovery,
vegetation,
and necessary
sudden flash
revisions within
floods
the
in some
dynamic
regions
field of
that reshaped
paleontology.
riverbeds,
These
and
diminutive
persistent
dinosaurs
volcanic
serve as a
activity
powerful
that could
reminder that the
periodically alter
prehistoric
local
world was
conditions
teeming with an
ashfall
incredible
and
array
lava
of
flows,
diverse creatures spanning
introducing
all
new
sizes,
challenges.
not solely
Within
the
these
towering
fluctuating
giants that so often
conditions,
dominate
other
our
successful
imagination.
reptilian
Their small
groups,
stature
distinct
likely
from true
enabled them to
dinosaurs,
occupy very
thrived
unique
in
and
various
specific ecological niches, further
These included
demonstrating the
the
remarkable
atosaurs,
adaptability
heavily
of
armored,
dinosaurs
pig-like
across the
herbivores
entirety
that
of their
superficially
incredibly long
resembled
reign on
scaly
Earth.
prehistoric
Dinosaurs,
tanks, browse
over
on
their
low-lying
extraordinary
vegetation,
160
and the
million year
large
reign,
crocodile-like
flourished
aquatic
across an
ambush
incredibly
predators with
diverse range
nostrils
of
located
global
unusually
environments,
high on their heads,
exhibiting a truly
perfectly adapted
remarkable
for lurking in
capacity for
ancient rivers and
adaptation.
swamps,
Their
waiting for
unparalleled
unsuspecting
success
prey.
was fundamentally
These
driven by the
non-dinosaurian
evolution of a
archosaurs were
vast
often
array
much
of
larger
unique
and more
physical
ecologically
characteristics
prominent than
and
the early
specialized
dinosaurs
behaviors,
themselves,
each
holding
finely
sway
tuned
over
to suit their
significant
specific
portions of the
habitats and
ecosystem.
ecological
Imagine a
roles.
young
In the parched,
Herrerasaurus,
arid
perhaps
regions of
only
the
a few
ancient
feet
world,
long,
some
carefully
dinosaurs
navigating a
developed
swampy
highly
floodplain,
efficient
its
physiological
keen sensors on
mechanisms for
alert,
water
keenly
conservation.
aware of the
The
lurking
long-necked
phytosaurs in the
sauropods,
murky
for instance,
water, or the
possessed
massive
immense
Rausuchians
barrel-shaped
patrolling the
bodies that
drier
could function
banks,
as
casting
biological
long
reservoirs,
shadows. The early
storing both
dinosaurs lived
water
in a
and
world
food
teeming
reserves
with
for
diverse,
extended
often
periods.
formidable
Their
competitors.
nostrils,
A
strategically
constant test of
positioned
their
high on their
evolutionary
heads,
advantages.
allowed them to
Their
breathe
initial
comfortably
success was not
even
about
while
brute
partially
force or
submerged in
overwhelming
water,
size, but
granting
about
them
subtle,
access to deeper
cumulative
aquatic
advantages.
sources.
Their more
For
upright
dinosaurs
stance allowed them
inhabiting
to
colder
breathe more
climates,
easily while
the
running,
evolutionary imperative
significantly
was
aiding their
insulation.
stamina in a pursuit
Certain
or escape,
species,
perhaps
such
a
as the
slightly
formidable
faster growth rate than their
tyrannosaurids,
rivals,
likely
allowing them
sported
to reach
feather-like
reproductive
coverings,
maturity
acting as
sooner,
natural
or a more
thermal
efficient
blankets to
metabolism,
retain body
giving them
heat.
an energetic
Others,
edge.
like
It
the
was this
duck-billed
quiet biological
hadrosaurs,
edge,
evolved
honed over
specialized
millions of
nasal
years of
passages
relentless
that
competition and
pre-warmed inhaled
adaptation
air before
that
it
allowed
reached
the
their
small,
lungs,
nimble
a
pioneers
crucial
to slowly,
adaptation
patiently
aiding their
carve out their
survival in cooler
irreplaceable place,
environments.
gradually paving
Coastal
the
and
way for
marine
the
adapted
majestic reign that was
dinosaurs,
still
a
millions of
truly
years in the
fascinating
future. A
subset,
faint whisper
developed
from the
distinct
Triassic
features
becoming an
tailored for life
undeniable
within
roar that
aquatic
would echo
realms.
across epochs.
Spinosaurus,
The
with its
evolution of the
elongated
upright
crocodile-like
stance itself,
snout
often
and
referred
specialized
to by
paddle-like tail,
biomechanists as
was exquisitely
parasitical
suited for
posture,
navigating and
was not a
hunting within
singular,
watery domains.
instantaneous
Its
evolutionary
dense, heavy
event,
bones
a
provided
sudden leap,
crucial
but
buoyancy
rather a
control,
gradual
enabling it to
continuum of
hunt effectively
adaptation,
within
a
rivers and
slow
swamps.
refinement over
These varied
countless
adaptations
generations.
powerfully
Early
underscore the incredible
archosaurs, the broader
diversity
group
and
that
profound
served as the
resilience of
precursors to
dinosaurs,
both dinosaurs
showcasing
and
their ability to
crocodilians,
thrive across an
typically
astonishing
exhibited a
spectrum
more
of
sprawling or
ecosystems throughout the
semi-erect
Mesozoic
posture,
era.
where their
The
limbs
geological
protruded outwards
phenomenon
from
of
their body
continental
before
drift
bending
played an
downwards,
absolutely
requiring
pivotal role in
significant effort
shaping
to
the
move.
grand
This allowed
evolutionary
for
of
effective
dinosaurs
but
over
often
millions
less
of years.
energy-efficient locomotion,
As the supercontinent
characterized by
Pangaea
a
slowly,
side-to-side bending of the
inexorably,
body that
began its
compressed their
majestic
lungs with every
process of
step.
fracturing
Over
and drifting
generations
apart,
within certain
roughly
key
230
lineages,
million years
natural
ago,
selective
it fundamentally
pressures strongly favored
reshaped the Earth's
individuals with
surface.
limbs positioned
This colossal
increasingly underneath the
geological
body.
transformation
This fundamental
systematically
shift in
created
limb
entirely
placement
new
drastically
environments,
improved both
and
endurance
critically,
burst
established
speed, with
formidable
limbs directly
geographical
supporting their
barriers.
weight.
These
The body
emergent
could be held
features
off the ground
profoundly
more
influenced the
effectively,
diversity
allowing
and
for
the global
respiration to
distribution
continue
patterns of
unimpeded and
dinosaurs.
efficiently during
The
sustained
gradual,
movement.
ceaseless
A
separation of
sprawling
these
animal,
colossal
by
land
contrast,
masses
might have
led
compressed
in
its
turn
lungs
to
with
the
each step,
isolation of previously
forcing it to stop
interconnected
periodically
dinosaur
and gasp for
populations.
air. A
This
costly
isolation
interruption.
acted as a
This
powerful
meant the early
evolutionary
dinosaurs,
catalyst,
with their evolving
compelling
upright
these
posture,
separated
could
populations
potentially
to
run
evolve
farther and
independently,
longer without
giving
tiring,
rise to
an
unique
invaluable
species,
asset for
each
relentless
exquisitely
hunting or making a
adapted to its
prolonged
specific
escape from
regional
danger.
environment.
Furthermore,
For
this
example, the
upright
profound profound
posture
geological
directly
separation
contributed to a
between what
more
would become
efficient
North
and
America
powerful
and
running
Eurasia
gait.
directly
The legs
contributed
could
to the
swing
emergence
forward
of
and
distinct
backward
and
in a more
unique
direct
dinosaurian
pendulum-like
lineages on
line
each
beneath the
continent.
body,
Concurrently, the
minimizing
dramatic
wasted
climate
energy
changes
from lateral
intimately linked with
movement and
continental
maximizing
drift also
forward
significantly
propulsion.
impacted This
dinosaur
fundamental
evolution.
biomechanical
As land
advantage
masses
allowed
slowly
them to
migrated
efficiently
across the
exploit
globe,
newly
they
available
experienced vastly
ecological
different
niches
weather
that
patterns
required
and
sustained
fluctuating
pursuit of
temperatures.
prey,
These
or
environmental
effective,
pressures
prolonged
forced
escape from
dinosaurs to
predators,
either adapt to
giving
these
them a
new
distinct
conditions
competitive
or
edge
embark on
over their more
migrations to more
sprawling
hospitable
rivals.
regions.
Imagine the
Some
silent,
areas
swift
became
pursuit
progressively
of an
more
early
arid,
theropod,
while others
its
transformed
slender
into
body
lush
held
tropical
high and stable
paradises,
above the
each
ground,
shift driving
its
the evolution of
powerful legs
specific
pumping in a
dinosaur
straight,
body types
efficient line,
and refined survival
contrasting
strategies.
sharply with the
The
laboured,
dynamic movement of
undulating,
continents
and less
also, at
energy-efficient
various
movements of a
geological
sprawling
junctures,
competitor.
created temporary
This
land
upright
bridges.
posture,
These fleeting
coupled with
connections
evolving
allowed dinosaurs
specialised
to
foot
migrate
structures,
between
such as a
previously
more
isolated
digitigrade
areas.
stance
This
walking on
intercontinental
toes
migration in
allowed for
turn
greater
intensified
agility,
competition among
enabling quicker
species
turns
and
and
spurred
more
further
precise
evolutionary
movements through
adaptations
varied
as
terrain,
various lineages
from
from
dense
different
forests
regions
to open
encountered and
plains.
interacted with
It was
one
a
another.
pivotal evolutionary
Continental
leap that
drift thus
fundamentally
acted as a
redefined
monumental,
terrestrial
powerful force,
locomotion,
meticulously
laying the
sculpting the
groundwork for
incredible,
incredible
breathtaking diversity
athleticism,
of
speed, and
dinosaurs that
ecological
thrived throughout the
diversity
entire
that would come to
Mesozoic
define
era.
the entire age
The
of
astonishing
dinosaurs. This
transformation of
quiet
dinosaurs
revolution in
into
movement,
birds
unfolding
stands as one of
slowly
the
in the
most
Triassic
captivating
dawn,
and
was a
profound
silent promise
evolutionary
of future
sagas in the
dominance,
entire
a subtle
history of life
advantage
on
that would
Earth.
ultimately
This
reshape the
intricate and
world.
gradual
As the
process
Triassic
commenced
period
approximately
gently drew to a
150
close,
million
and the
years
Earth
ago.
rotated
During
into
the
a new
vibrant
chapter,
Jurassic
the
period,
Jurassic period
certain
slowly
theropod
dawned,
dinosaurs,
ushering in what
specifically
many
those belonging to the
paleontologists
highly
consider the true
specialized
golden
group known
age
as
for dinosaurs.
Maniraptora,
This
began to
era,
exhibit and
spanning
develop
from
increasingly
approximately
bird-like
245
characteristics.
million
Over the
years
course of
ago,
millions
was
of years,
defined more
these
than any
particular
other by the
dinosaurs were already
undeniable and
equipped with
truly
remarkable
colossal presence of
features,
the
such as
sauropods.
hollow
These were
bones,
the long-necked,
which offered lightness,
plant-eating giants,
and feathers,
creatures
which
of such
initially
immense
served
scale
purposes
that
like
they
insulation
remain
and
even
visual
today
display.
the largest
As
land
the
animal
immense
to have ever
geological
walked the
clock
face of our
continued its
planet.
patient
They were the
ticking,
living mountains
these
of the
pre-existing
ancient world,
features began
their
to
forms
acquire
casting
entirely
long,
new and
moving
critical
shadows
functions.
across vast,
The feathers,
verdant landscapes.
originally
The
simpler
very ground
structures,
across
progressively
entire
became more
continents would tremble
complex,
faintly,
slowly developing into
continuously,
intricate,
beneath their ponderous
interlocking
rhythmic
forms
steps,
capable
a
of
subtle
generating
vibration
lift.
detectable
Concurrently,
perhaps
the
miles
bodies of
away
these
from their
evolving
path.
dinosaurs
The
underwent
sheer
a
scale and
significant
diversity of
transformation,
sauropods
becoming
during the
progressively
Jurassic was
smaller and
breathtaking.
lighter. Key
While all
adaptations
sauropods
for a
shared
more
the
airborne
fundamental
existence.
body plan of a
A
long
truly
neck,
pivotal development
massive
in this
torso, and
remarkable
long
transition
tail,
was the
they
gradual yet
diversified
profound
into a
transformation of
remarkable
their
array of
forearms
shapes,
into wings.
sizes, and
The delicate
ecological
wrist bones
niches,
began to
a
fuse,
testament
and
to
the number of
evolutionary
fingers gradually
ingenuity.
reduced,
They weren't a
collectively
monolithic
forming a
group,
robust and
but a
efficient
sprawling
support
family
structure
of
for the
giants.
increasingly
Consider
specialized
the
flight
differences.
feathers.
Some,
Simultaneously,
like the
their long
Diplodocids,
muscular
possessed
tails
exceptionally
shortened
long,
dramatically,
whip-like
eventually
tails and
evolving into
relatively
the compact
slender,
feathered tail
horizontal
seen in
necks,
modern birds,
optimized
which
for
serves as a
sweeping
crucial
vast swathes of
aerodynamic
low-lying
stabilizer.
vegetation,
Furthermore,
or perhaps
their ancient
stripping
teeth
leaves
were,
from taller
over
trees.
time, gradually
Imagine a
replaced by lightweight,
Diplodocus,
versatile
its head
beaks,
often
capable of
positioned just
efficiently
15
handling
feet
a
off the
diverse
ground in
range
a
of
typical
diets.
grazing
This
posture,
entire evolutionary
but capable of
process
raising its
was
head
by
to
no
an
means
astonishing 30
instantaneous.
feet if
It was
reaching
a
for
slow,
specific
deliberate
foliage.
march of gradual
Others, such as
changes,
the
unfolding over millions of
epitomized
years,
by Brachiosaurus
punctuated by
and
numerous
Giraffatitan,
intermediate species
evolved
that
with much
served as
shorter,
crucial
deeper
bridges
tails and
between
necks that
dinosaurs and
angled
birds.
sharply upward,
The celebrated
allowing them
fossil
to
of
browse at
Archaeopteryx,
incredible
discovered in
heights,
Germany,
their heads often
perfectly
towering
embodies
over
one
40
such
feet
transitional
above the
form,
ground in a natural
showcasing a
stance.
remarkable
This
mosaic
niche
of both
partitioning
definitive
by height was
dinosaurian
crucial.
and distinctly
It allowed
avian
different
features.
sauropod
Through the
species to
relentless and
coexist in the
guiding
same
hand of natural
environments without
selection,
direct
those
competition for
individuals
the
best
exact
adapted
same
for
food
flight
sources,
survived and successfully
enabling
passed
vast
on their
herds to share the
advantageous
same
genes,
forests.
ultimately
An average
culminating in the
Jurassic
astonishing and
sauropod herd
diverse
based
array
on
of birds that
hypothetical
grace our
population
skies
density
today.
models
The
might have
profound and
consisted of 30
undeniable
to 50
connection between
individuals,
dinosaurs
ranging
and
from
birds
immense adults
is
to
not
nimble
merely a theory,
juveniles,
it is
consuming
supported by an
collectively several tons
overwhelming
of
wealth
plant
of
matter each
compelling
day.
evidence,
Let's delve
meticulously
into some
gathered from a
specific
multitude of
examples
scientific
these Jurassic
disciplines.
titans.
Fossil records
iconic
provide an invaluable
Diplodocus, a
cornerstone,
majestic
meticulously
sauropod,
revealing countless
primarily known
dinosaur
from the Morrison
species adorned with
Formation in western
unmistakably
North
bird-like
America,
features.
was a creature
These
of
precious
immense
remnants
length,
include
though not
exquisitely
necessarily the
preserved hollow
heaviest.
bones,
It could stretch
familiar
to an
wishbones,
astonishing 90
and even
feet
feathers
long,
captured
with
in
its
stunning
whip-like
detail.
tail alone
The
accounting
discovery
for
of
nearly half of
Archaeopteryx,
that length.
often heralded
This
as a
tail,
quintessential
composed of
transitional
approximately 80
fossil,
caudal
serves as a
vertebrae,
powerful
was not merely
testament,
a counterbalance.
showcasing a creature that
Biomechanical
seamlessly blends
analysis suggests
both
it
distinct
could have been cracked
dinosaurian
like a
and
whip
clear
at
avian
supersonic
characteristics,
speeds,
thereby
potentially
bridging a
producing
critical
startling
evolutionary
200
gap.
decibel
Anatomical
sonic boom
studies
to
have
ward
further
off
illuminated
predators,
this
or
deep
communicate
relationship,
across vast
exposing
distances,
striking
a sound like
resemblances
a
in
distant
skeletal
clap of
structure
thunder.
between
Its
certain
head
dinosaur
surprisingly
groups and
small
modern
for its
birds,
body, The characteristic three-toed foot observed in many theropod dinosaurs, for instance, bears a remarkable similarity to that of birds, and both lineages share a unique wrist joint that permits the folding of their forelimbs. Moreover, the microscopic examination of fossilized bones reveals analogous growth patterns and internal structures in both dinosaurs and birds, reinforcing their shared heritage. Behavioral evidence also lends robust support to this connection. Certain dinosaur species, such as the oviraptor, have been found fossilized in brooding postures atop nests, a nurturing behavior intrinsically characteristic of modern birds. Trace fossils of dinosaur nests and eggs exhibit striking resemblances to those of contemporary avian species. Furthermore, analyses of dinosaur brain casts suggest that some species possess the neurological capacity for complex behaviors often associated with birds, including the intricate demands of flight and advanced visual processing. Finally, genetic research has provided profound molecular confirmation of the dinosaur-bird link. While dinosaur DNA itself is too degraded for direct analysis due to its immense age, studies of ancient proteins extracted from dinosaur fossils have undeniably shown molecular similarities to those found in modern birds. This powerful confluence of molecular, anatomical, behavioral, and fossil data presents an ironclad case for the evolutionary relationship between dinosaurs and birds, firmly establishing the theory that birds are in essence the living descendants of dinosaurs. Dinosaurs possessed a truly remarkable and diverse array of skeletal features, elements that profoundly distinguish them from all other reptilian forms. One of their most distinctive and crucial traits was their upright posture, an evolutionary innovation where their limbs were positioned directly underneath their bodies, rather than sprawling outwards to the sides as seen in many other reptiles. This fundamental structural alteration permitted significantly more efficient movement across land and, perhaps even more importantly, provided the necessary robust support for their often truly colossal body weights. The dinosaur skull itself was a marvel of evolutionary diversity, its morphology varying enormously from one species to another. Many possessed noticeably large eye sockets, suggesting acute vision, and spacious nasal passages. Some, in a dramatic display of adaptation, even developed elaborate crests or formidable horns. Their powerful jaws were frequently lined with an impressive array of sharp, replaceable teeth, each perfectly adapted to their specific dietary needs, whether they were consuming tough vegetation or tearing through raw flesh. The vertebral column of dinosaurs represented another key anatomical feature, with some species exhibiting impossibly long necks that stretched towards ancient canopies, or sweeping tails that served a multitude of purposes. These varied spinal adaptations facilitated everything from reaching high-lying foliage to providing crucial balance and serving as potent defensive mechanisms. Many dinosaurs also evolved highly specialized hip structures, such as the bird-like arrangement observed in theropods, a configuration that remarkably later served as the direct evolutionary blueprint for modern birds. Perhaps most famously, certain dinosaur groups developed impressive body armor, including thick dermal plates, menacing spikes, and bony osteoderms embedded within their skin. These formidable structures offered vital protection from the predatory behemoths of their era, and may also have played nuanced roles in temperature regulation or elaborate display. The intricate combination of these unique skeletal features collectively enabled dinosaurs to achieve and maintain their unparalleled dominance over terrestrial ecosystems for an extraordinary period of over 160 million years, profoundly showcasing the incredible adaptability and boundless diversity of these ancient reptilian giants. The fundamental body plans of dinosaurs exhibited truly dramatic variation across their myriad species, each form elegantly reflecting their unique lifestyles and specific evolutionary adaptations. The two principal groupings of dinosaurs, the Saurischians and the Ornithischians, possess distinctly different hip structures, and these subtle anatomical differences profoundly influence their overall body shapes and modes of locomotion. Theropods, a terrifyingly efficient group that included the iconic Tyrannosaurus rex, were primarily bipedal predators. Their bodies were typically characterized by powerful hind legs, equipped with sharp claws for gripping, and teeth meticulously designed for the efficient hunting and consumption of prey. Their forms were often streamlined, optimized for speed and agility, typically featuring relatively small forelimbs and a long muscular tail that acted as a crucial counterbalance. In stark contrast, the sauropods, such as the towering Brachiosaurus, presented a radically different architectural design. They were characterized by their massive pillar-like legs, which served as immense weight-bearing columns, supporting incredibly long necks and disproportionately small heads. This unique combination allowed them to reach and strip vegetation from the highest reaches of ancient forests. The Ornithischian dinosaurs, a highly diverse group, showcased an even broader spectrum of body plans. The majestic Triceratops, for instance, boasted an enormous frilled head adorned with formidable horns and a sharp parrot-like beak, used for both defense and efficient foraging. Stegosaurs, instantly recognizable, featured a distinctive double row of upright bony plates along their backs, complemented by a tail armed with menacing spikes for protection. The ankylosaurs, true living fortresses, developed heavy, intricate armor plating across their bodies and wielded a formidable club-like weapon at the end of their tails. Furthermore, some dinosaurs evolved highly specialized features tailored precisely for their specific environments. Spinosaurus, for example, possessed a unique sail-like structure on its back and exhibited clear anatomical adaptations indicative of a semi-aquatic lifestyle, suggesting it spent considerable time in water. These immensely varied body plans collectively stand as a testament to the astounding diversity and unparalleled adaptability of dinosaurs, enabling them to thrive across the globe throughout their immensely long reign on Earth. The hip structures of dinosaurs were not merely incidental features. They were defining anatomical characteristics that unequivocally distinguished them from other reptiles, and moreover, played an absolutely crucial role in their fundamental scientific classification. These ancient, magnificent creatures displayed two markedly distinct hip configurations, which subsequently became the very foundation for dividing them into their major evolutionary groups. The first of these, known as the lizard hip structure, was the hallmark characteristic of the Saurischian dinosaurs. This specific configuration featured a pubis bone that pointed distinctly forward, a skeletal arrangement remarkably similar to that observed in modern lizards. Within this group resided formidable theropods, like the iconic Tyrannosaurus rex, known for their powerful bipedal stride, and the towering sauropods, such as the colossal Brachiosaurus, with their immense quadrupedal forms. The second type, conversely, was termed the bird hip structure, and this was exclusively found in the Ornithischian dinosaurs. In this particular arrangement, the pubis bone pointed backward, lying parallel to the ischium. It's a fascinating evolutionary twist that this hip structure bears a striking resemblance to that of modern birds, even though birds, in an unexpected turn of events, actually evolved from the theropod lizard-hipped dinosaurs, rather than from the bird-hipped ornithischians themselves. Dinosaurs such as the heavily armored Stegosaurus and the iconic three-horned Triceratops belong to this ornithischian group. These uniquely evolved hip structures were paramount, as they allowed dinosaurs to develop an astonishing diversity of body plans and specialized locomotion styles. This anatomical innovation was a key contributor to their immense success and their unparalleled dominance for an incredible span of over 160 million years. The specific hip configurations fundamentally influenced how individual dinosaurs moved, how they maintained their often precarious balance, and even how they reproduced, ultimately sculpting their intricate evolution and their profound adaptation to the various ever-changing environments that characterize the Mesozoic era. The evolution of dinosaur legs and feet represents a remarkable saga of adaptation, unfolding over millions of years and resulting in an astonishing array of locomotion styles, each perfectly suited to their diverse environments and unique lifestyles. The very earliest dinosaurs, the pioneers of their lineage, likely walked on two legs, exhibiting a bipedal stance, with feet possessing three distinct toes, a design somewhat akin to their more primitive ancestors. From this foundational blueprint, the limbs of dinosaurs diversified with astonishing creativity, evolving into a vast spectrum of specialized forms. The theropods, that fearsome and diverse group, encompassing carnivorous dinosaurs and, surprisingly, modern birds, steadfastly retained and meticulously refined their bipedal locomotion. Their legs underwent a profound transformation, becoming increasingly bird-like, characterized by a distinct backward-pointing knee joint and a digigrade stance, meaning they walked primarily on their toes. This highly efficient design conferred immense advantages in terms of speed and agility, qualities that were absolutely crucial for their predatory lifestyles.
Some theropods further optimize their running capabilities by developing elongated metatarsals, essentially forming a third segment to their lower leg, which dramatically enhanced their burst speed and sustained running abilities. In stark contrast, the sauropods, the colossal long-necked herbivores, evolved immensely strong column-like legs, meticulously designed to bear their truly enormous body weight. Their feet, accordingly, developed a more plantigrade posture, where their immense weight was broadly distributed across the entire foot, often including a thick, fleshy pad. This adaptation was essential, allowing them to carry their immense bulk with remarkable efficiency across various terrains. Some sauropods even possessed claws on their feet, which might have served for defense or to gain better traction on softer ground. The ornithischians, a varied group including the horned and armored dinosaurs, perhaps showcased the greatest diversity in leg structure. While some members of this group remained bipedal, many others evolved robust quadrupedal stances. The ceratopsians, with their heavy frilled heads, developed legs that splayed slightly outward, providing a stable, wide platform to support their considerable cranial mass. Ankylosaurs, the heavily armored living tanks, had short, sturdy legs, built to support their formidable protective bodies, and the hadrosaurs, the renowned duck-billed dinosaurs, retained the remarkable ability to switch between bipedal and quadrupedal movement, with specialized wrist bones that allowed them to walk efficiently on all fours when the need arose. This sheer variety in limb and foot structure stands as a powerful testament to the boundless adaptability of dinosaurs across their vast evolutionary history.
Dinosaur crests and frills were truly extraordinary anatomical features, serving a multitude of complex purposes for these ancient creatures. These often ornate structures, prominently displayed on various iconic species such as the three-horned Triceratops and the distinctive Parasaurolophus, played absolutely crucial roles in their daily lives and intricate social interactions. One of the primary functions attributed to this elaborate headgear was visual communication. The crests and frills acted as striking, visually arresting displays. These could be strategically employed to attract potential mates, to intimidate formidable rivals within their own species, or to simply identify members of the same specific group from a distance. These elaborate structures often underwent significant growth and became more vibrantly colored as dinosaurs reached their sexual maturity, strongly suggesting their immense importance in the complex rituals of courtship. Beyond mere display, these features likely also served as sophisticated thermoregulatory devices. The large surface area of these crests and frills, crisscrossed with an intricate network of blood vessels, could have effectively assisted dinosaurs in regulating their internal body temperature. They could absorb warmth when basking in the sun, or, conversely, dissipate excess heat in cooler environments or when overheating, perhaps after a strenuous chase. This physiological adaptation would have been particularly advantageous for maintaining optimal body temperature across varying climatic conditions. Furthermore, scientists have provocatively proposed that some crests may have functioned as natural resonating chambers, capable of amplifying vocalizations and allowing dinosaurs to produce a wider, more complex range of sounds for communication. This captivating theory holds particular relevance for hollow-crested species, such as Parasaurolophus, whose elaborate head ornaments might have indeed acted as a form of natural biological sound amplifier, enabling them to communicate across vast distances in their ancient world. The dental structures of dinosaurs were remarkably diverse, a direct reflection of the wide array of diets these ancient creatures consumed throughout their reign. Carnivorous dinosaurs exemplified this specialization, possessing formidable arrays of sharp, often serrated teeth, meticulously designed for the brutal tasks of tearing flesh and crushing bone. These teeth were frequently curved and shaped like daggers, allowing apex predators to effectively grip and rip into their struggling prey. The teeth of renowned carnivores like the mighty Tyrannosaurus rex could individually grow to an astonishing 12 inches in length, rendering them absolutely formidable weapons for both hunting and feeding. In stark contrast, herbivorous dinosaurs sported teeth that were exquisitely adapted for the painstaking process of grinding and chewing tough plant material. Many of these plant eaters, such as the towering long-necked sauropods, had simpler peg-like teeth, perfectly suited made for stripping leaves directly from branches with minimal effort. Others, like the distinctive duck-billed hadrosaurs, developed incredibly complex dental batteries consisting of hundreds of teeth packed tightly together in a mosaic-like arrangement. These numerous teeth would continuously grow and replace themselves throughout the dinosaur's life, providing an ever-renewing grinding surface for efficiently breaking down fibrous vegetation. Such hadrosaurs could at any given moment possess up to 800 teeth in their mouths, a true testament to their specialized diet. Some herbivores, including the horned ceratopesians like Triceratops, even featured beak-like structures at the front of their mouths, composed of keratin, which allowed them to snip off plants. These beaks were then complemented by rows of leaf-shaped teeth further back, ideal for slicing and grinding. This remarkable combination allowed them to process a wide variety of plant materials with immense efficiency. The profound differences in tooth structure between carnivores and herbivores provide invaluable insights into the distinct ecological roles that dinosaurs played within their ancient ecosystems. Interestingly, some dinosaurs even evolved highly specialized teeth for truly unique diets. The Therizinosaurus, for example, despite its theropod lineage, possessed small leaf-shaped teeth, strongly suggesting a herbivorous diet. This sheer dental diversity powerfully highlights the remarkable evolutionary paths dinosaurs undertook to exploit a vast spectrum of different food sources in their ancient environments. Our knowledge regarding the internal organs of dinosaurs, while certainly limited, has seen significant advancements through the painstaking and meticulous analysis of fossilized remains. Given that soft tissues very rarely survive the fossilization process, much of what we infer about their internal anatomy comes from a combination of studying their skeletal structures, drawing comparative anatomical parallels with modern animals, and in exceptionally rare instances, finding remarkably preserved internal features. One of the most intriguing and pivotal discoveries concerns dinosaur lungs. A growing body of evidence strongly suggests that many dinosaurs, particularly the agile theropods and the colossal sauropods, possessed a highly complex respiratory system. This system bore striking similarities to the incredibly efficient respiratory apparatus found in modern birds. It likely incorporated a series of interconnected air sacs that extended even into their hollow bones. This adaptation would have allowed for a far more efficient uptake of oxygen, which in turn may have been a critical factor contributing to their astonishing ability to grow to such enormous sizes. The question of dinosaur hearts has also been a subject of considerable scientific inquiry. While no perfectly preserved complete dinosaur heart has ever been definitively discovered, careful analysis of their chest cavities and the arrangement of their rib cages strongly indicates that dinosaurs probably possessed four-chambered hearts. This complex cardiac structure is characteristic of modern birds and mammals. Such an advanced heart would have been essential for supporting their active lifestyles and maintaining the high metabolic rates necessary for their immense energy demands. Regarding their digestive systems, the discovery of fossilized stomach contents, known scientifically as coprolites, has provided invaluable direct insights into dinosaur diets and their digestive processes. For instance, some herbivorous dinosaurs, such as the immense sauropods, likely harbored large, highly complex digestive tracts, necessary for the slow, thorough processing of tough plant material. Carnivorous dinosaurs, on the other hand, likely possessed shorter, more acidic digestive systems, optimized for the rapid breakdown and absorption of meat. The respiratory systems of dinosaurs were remarkably efficient, setting them apart from the breathing mechanisms found in many modern animals. These ancient creatures possessed a unique and sophisticated arrangement of air sacs and lungs that facilitated a continuous, unidirectional flow of oxygen-rich air through their bodies. This ingenious system was significantly more effective than the bidirectional breathing process observed in mammals today, where inhaled and exhaled air mix in the lungs. The dinosaur respiratory apparatus consisted of multiple air sacs strategically connected to highly specialized lungs. Upon inhalation, fresh oxygenated air would first flow into posterior air sacs, located towards the tail end of the dinosaur's body. During exhalation, this air would then be shunted from these posterior sacs into the lungs, where the vital exchange of gases, oxygen intake and carbon dioxide release occurred.
Simultaneously, the air that had already passed through the lungs during the previous breath cycle would be expelled from the body via anterior air sacs, situated closer to the head. This ceaseless, continuous current of air ensured that a supply of oxygen-rich air was constantly traversing the lungs, maximizing oxygen extraction and profoundly enhancing overall respiratory efficiency. Such a highly effective system undoubtedly contributed to the impressive size and active, often energetic lifestyles of many dinosaur species, enabling them to thrive even in the potentially lower oxygen environments that characterized parts of the Mesozoic era. What is truly fascinating is that this sophisticated respiratory system is not entirely lost to the annals of time. Modern birds, the direct living descendants of certain dinosaur lineages, have retained a remarkably similar breathing mechanism. This profound evolutionary legacy provides us with invaluable insights into how dinosaurs might have breathed, and serves to help explain their remarkable and sustained success over millions upon millions of years. Sauropod dinosaurs possess truly unparalleled necks, a feature that unequivocally distinguished them from any other creature known to have existed in Earth's long and varied history. These colossal plant eaters, a group that included such iconic species as the magnificent Brachiosaurus and the elongated Diplodocus, sported necks of extraordinary length, often extending to an incredible 40 feet or even more. This astonishing anatomical feature granted them the unique ability to reach and consume vegetation high in the treetops, or to gracefully sweep across vast stretches of land, grazing without the necessity of moving their immense bodies. The biological secret underpinning these impossibly elongated necks lay within their distinctive bone structure. The cervical vertebrae of sauropods were astonishingly permeated with air sacs, rendering them surprisingly lightweight despite their considerable dimensions. This remarkable adaptation allowed these giants to support and precisely maneuver their lengthy necks without enduring excessive structural strain. Furthermore, these integrated air sacs were intimately connected to their respiratory system, significantly enhancing their breathing efficiency and contributing to their capacity for thermoregulation, helping to control their body temperature. Another captivating aspect of sauropod necks was their impressive flexibility. Unlike mammals, which typically possess a mere 7 neck vertebrae, sauropods could boast up to 19 vertebrae in their cervical column. This increased number of individual joints provided them with an unparalleled range of motion, enabling them to arch and bend their necks in ways that would be utterly impossible for any modern animal. The clear evolutionary advantage of these specialized necks was undeniable. They provided sauropods exclusive access to vast food sources that remained entirely out of reach for all other herbivorous creatures. This pivotal adaptation played an absolutely crucial role in their immense success, allowing them to dominate terrestrial ecosystems for over 100 million years, ultimately making them some of the largest land animals ever to grace the face of the earth. The forelimbs of theropod dinosaurs underwent a truly fascinating and profound evolutionary journey across millions of years, meticulously adapting to a diverse array of lifestyles. Beginning with the early theropods, such as the nimble Herrerasaurus, these ancestral dinosaurs possessed relatively long, dexterous arms, armed with sharp claws that were undoubtedly effective for seizing and firmly holding onto struggling prey. As the theropod lineage diversified, their arm structures began to change dramatically, each modification meticulously tailored to specific hunting strategies and ecological roles. In certain lineages, most famously exemplified by the iconic Tyrannosaurus rex, the arms became drastically reduced in size. These immensely powerful predators relied predominantly on their massive, bone-crushing skulls and their robust, powerful hind legs for subduing prey, rendering their forelimbs less critical for hunting. However, it's important to note that even these seemingly diminutive arms were likely not entirely useless. They could have potentially served subtle functions in elaborate mating displays, or perhaps aided the colossal animal in pushing itself up from a prone position. Other theropod groups, however, propelled arm evolution in an entirely opposite direction. The direct ancestors of modern birds, such as the formidable Deinonychus and the swift Velociraptor, developed noticeably longer, more flexible arms, endowed with features that would ultimately pave the way for powered flight. These elongated arms bore intricate feathers and exhibited an increased range of motion at the shoulder joint, meticulously setting the anatomical stage for the eventual development of true wings. Perhaps most intriguingly, some theropods, like the bizarre Therizinosaurus, evolved truly massive curved claws on their elongated arms. These highly unusual appendages were, surprisingly, likely not primarily used as weapons for hunting, but rather served unique purposes, such as pulling down branches to feed on dense vegetation. This adaptation allowed them to access food sources that might have been out of reach for other herbivores, showcasing the incredibly diverse and sometimes unexpected roles that theropod arms could fulfill beyond mere predation. This remarkable diversity in arm structure powerfully underscores the unparalleled adaptability of theropods throughout their incredibly long and dynamic evolutionary history. Paleontologists, through meticulous study of both fossilized bones and intriguing trace fossils, have uncovered utterly fascinating evidence pertaining to the social behavior of dinosaurs. One of the most compelling pieces of this ancient puzzle comes from dinosaur trackways, preserved sequences of footprints that clearly show multiple individuals of the same species moving in a coordinated parallel direction. These fossilized parades strongly suggest that some dinosaur species, particularly the vast herds of herbivores, traveled in cohesive groups, likely for mutual protection against formidable predators or during arduous seasonal migrations. The discovery of fossilized nesting sites offers another profound window into the complex social structures of dinosaurs. Extensive nesting grounds, particularly associated with certain species of hadrosaurs and sauropods, indicate that these dinosaurs may have consistently returned to the same communal breeding areas year after year. This recurring behavior hints at a significant level of social organization and potentially even a degree of cooperative care for their young. Bone beds, which are sites where multiple skeletons of the same dinosaur species are found densely packed together, provide further compelling clues about social behavior. Some of these sites contain the remains of numerous individuals, suggesting mass mortality events that struck entire herds, reinforcing the likelihood of herding behavior. For instance, ceratopsians, such as Centrosaurus, have been found in truly massive bone beds, strongly implying that they lived and tragically died in large communal groups. Certain dinosaur species also exhibit tantalizing evidence of pack hunting behavior. The agile Deinonychus, a relatively small dromaeosaurid, has been found in close association with the remains of much larger prey animals. This remarkable finding suggests that these nimble predators may have actively collaborated to bring down prey significantly larger than themselves, much like modern wolves or lions operate in coordinated hunting packs today. While the interpretation of complex behaviors from static fossils necessarily requires a degree of scientific caution, these converging lines of evidence paint an increasingly vivid picture of surprisingly complex social interactions among many dinosaur species. Dinosaurs, much like the myriad animals that populate our world today, exhibited a wide and varied range of intelligence levels. Recent groundbreaking research powerfully suggests that certain dinosaur species were, in fact, considerably more intelligent than had been previously assumed. For example, the troodon, a relatively small carnivorous dinosaur, possessed a remarkably large brain in proportion to its overall body size, a ratio quite comparable to that observed in modern birds. Many dinosaurs, particularly those within the theropod group, which notably includes species like the agile velociraptor and the formidable Tyrannosaurus rex, displayed compelling signs of complex behaviors. These sophisticated activities encompassed coordinated pack hunting, dedicated parental care for their offspring, and even in some intriguing cases, the apparent use of simple tools. Such intricate behaviors inherently demand a certain level of problem-solving ability and a degree of social intelligence. However, it is crucial to emphasize that brain size, by itself, is not the sole determinant of intelligence. The internal structure and inherent complexity of the brain also play absolutely pivotal roles. Some herbivorous dinosaurs, despite possessing relatively smaller brains in comparison to their immense body mass, likely commanded the necessary intelligence to navigate the intricate social hierarchies within their expansive herds. When considering comparisons to modern animals, the intelligence level of many dinosaur species might be aptly likened to that of present-day birds and certain reptiles. This comparison is particularly pertinent given the established fact that birds are the direct, living descendants of specific dinosaur lineages. While it is true that dinosaurs may not have attained the advanced cognitive levels of the most intelligent modern mammals, they were undeniably far removed from the sluggish, dim-witted creatures so often portrayed in earlier popular culture. Fossilized footprints, silent impressions left in the ancient mud, offer paleontologists an utterly unique and invaluable window into the daily lives and complex behaviors of dinosaurs. These preserved tracks, often referred to by scientists as trace fossils, reveal far more than just the simple shape of a dinosaur's foot. They provide an astonishing direct glimpse into the distant past, showing us the precise speed at which dinosaurs moved, their particular gait, and even incredibly nuanced details about their social interactions. By meticulously studying the precise distance between individual footprints, scientists can accurately calculate the stride length of different dinosaur species. This vital piece of information, when thoughtfully combined with expert estimates of leg length derived from skeletal remains, allows researchers to determine with remarkable accuracy how fast these magnificent creatures were moving when they left their indelible marks. Some trackways, for instance, portray dinosaurs moving at a remarkably leisurely walk, a slow, deliberate pace. Others, however, provide compelling evidence that they were capable of running at considerable, even surprising speeds. The specific arrangement of footprints within a trackway also offers profound insights into a dinosaur's posture and overall gait. For example, the relatively narrow trackways left by some of the largest sauropods, those immense long-necked giants, strongly suggest that these colossal creatures walked with a column limb posture, a weight-bearing stance remarkably similar to that of modern elephants. In stark contrast, the wider trackways left by certain theropods indicate a far more dynamic and agile gait, with their legs positioned directly beneath their bodies, allowing for faster, more powerful and more agile movement. Perhaps most intriguingly, the discovery of multiple trackways found closely together can illuminate complex social behaviors. Parallel trackways, featuring individuals of similar size moving in unison, strongly suggest that some dinosaur species, particularly the vast herds of herbivores, traveled in cohesive groups or even tight-knit family units. In exceptionally rare and thrilling cases, trackways have even preserved compelling evidence of ancient predator-prey interactions, with the distinctive footprints of a carnivorous dinosaur intersecting those of potential prey species. These fossilized scenes are like dramatic snapshots of prehistoric life, frozen in time, helping to paint an ever more complete and vivid picture of the incredibly complex ecosystems that thrived millions of years ago. These enduring marks, etched into the very stone of the earth, truly bring the prehistoric world to life in ways that continue to capture our collective imagination and deepen our profound understanding of these fascinating ancient creatures. Dinosaur tails played an absolutely crucial and multifaceted role in the complex locomotion of these ancient creatures, serving a variety of functions that varied significantly depending on the particular species. For many dinosaurs, especially the immense long-necked sauropods and the agile bipedal theropods, the tail functioned as a vital counterbalance to the substantial weight of the front portion of their bodies. This counterbalancing effect was unequivocally essential for maintaining stability and ensuring proper balance, whether they were simply walking or engaged in a powerful, swift run. In theropod dinosaurs such as the iconic Tyrannosaurus rex, the tail filled with powerful muscles helped to shift their center of gravity backward, a critical adaptation that allowed them to stand upright and maintain equilibrium on their two robust legs. As these formidable dinosaurs moved, their muscular tails would rhythmically sway from side to side, providing dynamic momentum and critically aiding in rapid changes of direction. This constant controlled tail movement also contributed significantly to the conservation of energy during locomotion, making their movements remarkably efficient. For the quadrupedal dinosaurs, those that walked on all four legs, like the plate-backed Stegosaurus and the heavily armored Ankylosaurus, their tails served a dual purpose. They acted both as a crucial counterbalance for stability and as a formidable defensive weapon, while walking their ponderous tails would have moved in a broad, sweeping motion, further contributing to their overall stability. Some scientists have even hypothesized that certain dinosaur species may have utilized their tails as rudimentary rudders when swimming, guiding their movement through water, though this intriguing idea remains a topic of ongoing research and scientific debate. More recent, cutting-edge studies have also provocatively suggested that some dinosaurs, particularly the smaller, more agile species, may have actively used their tails to generate additional thrust during running. By powerfully swinging their tails up and down, these dinosaurs could have significantly increased their speed and enhanced their agility, much in the same way that modern cheetahs utilize their tails for swift turns and explosive acceleration. This incredible versatility in tail function profoundly highlights its fundamental importance to the diverse and dynamic movement of dinosaurs. Certain dinosaurs, in a remarkable testament to evolution's ingenuity, developed truly astonishing adaptations for existing within aquatic environments. Spinosaurus, a gargantuan carnivore and one of the largest predatory dinosaurs ever discovered, stands as a prime example. This semi-aquatic behemoth evolved uniquely dense bones which would have counteracted buoyancy, allowing it to submerge itself more effectively. Its feet, surprisingly, were paddle-like, clearly aiding in powerful swimming and agile maneuvering through ancient waters. Its elongated crocodile-like snout, filled with conical teeth, was perfectly suited for swiftly catching fish and other aquatic prey, while its nostrils were positioned high on its skull, a critical adaptation that enabled it to breathe even while its massive body was largely submerged. Other dinosaurs, such as the duck-billed hadrosaurs, possessed webbed hands that likely functioned as effective paddles, helping them navigate through water. Some paleontologists even believe these creatures were highly skilled swimmers, capable of effortlessly traversing wide rivers and vast lakes. Their powerful muscular tails, often laterally flattened, could have served as incredibly effective propulsion mechanisms in aquatic settings, driving them through the water with considerable force. The Nyctosaurus, a type of pterosaur, often mistakenly lumped with dinosaurs, had uniquely shaped wings that some scientists theorize were specifically adapted for skimming across water surfaces, allowing it to snatch fish. This specialized feeding technique, reminiscent of certain modern seabirds, would have enabled it to feed with remarkable efficiency in marine environments. These remarkable adaptations vividly highlight the diverse and creative ways dinosaurs evolved to exploit every available ecological niche, including aquatic ones. They underscore their incredible capacity to thrive across a vast spectrum of environments throughout the Mesozoic era. As new fossils continue to be unearthed and existing specimens are subjected to ever more sophisticated analysis, our understanding of dinosaur adaptations for aquatic life continues to expand and evolve, revealing an even richer tapestry of prehistoric existence. Dinosaur hip structures, far from being a mere anatomical detail, played an absolutely crucial role in shaping their distinctive gaits and fundamentally influenced how these ancient creatures moved and interacted within their diverse environments. The scientific classification of dinosaurs prominently highlights two main types of hip configurations: the lizard-hipped and the bird-hipped arrangements. Lizard-hipped dinosaurs, formerly known as saurischians, possessed a hip structure that allowed for notably greater leg mobility. This enhanced range of motion enabled them to take longer, more powerful strides and potentially move with greater speed and agility. Theropods, a group encompassing the iconic and fearsome Tyrannosaurus rex, belong to this lizard-hipped category. They often exhibited a more upright posture, with their powerful legs positioned directly beneath their bodies, optimized for running and striking. In contrast, bird-hipped dinosaurs, or ornithischians, featured a hip structure that resulted in a distinctly different gait. Their legs were typically positioned slightly outward from their bodies, creating a broader, more stable stance. This arrangement, while providing excellent stability, generally resulted in slower, more deliberate movement compared to their lizard-hipped counterparts. Many herbivorous dinosaurs, such as the armored Stegosaurus and the formidable Triceratops, belong to this bird-hipped group. The profound differences in these hip structures and the resulting variations in their gaits had immensely significant implications for dinosaur behavior and their ecological roles. Lizard-hipped dinosaurs were often better suited for swift pursuit and active predation,
are designed for hunting success. Conversely, bird-hipped dinosaurs typically evolved adaptations that favored strong defense mechanisms and highly efficient consumption of plant matter. These distinct locomotion styles collectively sculpted the incredibly diverse roles dinosaurs played within their complex and ancient ecosystems, each gate a silent testament to millions of years of evolutionary refinement. Paleontologists have developed several compelling theories regarding the stamina and endurance of dinosaurs, basing their insights on meticulous fossil evidence and insightful comparisons with modern animal physiology. One prominent and increasingly accepted theory suggests that many large dinosaurs, particularly the gargantuan long-necked sauropods, were likely warm-blooded, or at least mesothermic, and therefore capable of sustained high-level activity. This revolutionary idea is strongly supported by the microscopic structure of dinosaur bones, which often display growth patterns remarkably similar to those observed in active endothermic animals like modern mammals and birds. Another key theory focuses on the highly advanced respiratory systems of dinosaurs. Some scientists hypothesize that certain dinosaurs, especially powerful theropods such as Tyrannosaurus rex, possessed incredibly efficient bird-like air sac systems. This sophisticated breathing mechanism would have enabled a far more effective uptake of oxygen, potentially allowing for significantly higher levels of stamina and endurance during strenuous physical activities like relentless hunting or extensive long-distance migrations. The very shape and specific arrangement of dinosaur leg bones have also provided fertile ground for theories about their endurance capabilities. Certain studies suggest that some dinosaurs, particularly ornithopods like Iguanodon, possessed leg structures that were exquisitely well suited for efficient, sustained movement. This adaptation might have empowered them to cover vast distances in their relentless search for food or to escape from formidable predators. However, it's important to note that not all dinosaurs are believed to have been built for such prolonged endurance. Some theories propose that heavily armored dinosaurs, such as the ankylosaurs and stegosaurs, may have had considerably lower stamina due to their immense body mass and the sheer energetic cost required to move their heavy protective plates and spikes. These armored giants might have relied more on short explosive bursts of activity, perhaps for defense, rather than prolonged exertion. The foot structure of dinosaurs exhibited truly remarkable diversity across their different species, elegantly reflecting their varied lifestyles and the specific environments they inhabited. Theropods, the agile and fearsome group that included iconic carnivores, like the Tyrannosaurus rex, typically possessed 3 forward-facing toes, each armed with sharp claws. These feet were perfectly designed for gripping struggling prey and crucially for maintaining balance while engaged in rapid running. Their feet were often narrow and elongated, an adaptation that facilitated swift movement and agile hunting maneuvers. In stark contrast, the feet of immense herbivorous sauropods, such as the towering Brachiosaurus, were more reminiscent of those found on modern elephants. Their feet were broad and remarkably flat, with 5 toes arranged in a semicircular pattern. This robust structure effectively helped to distribute their immense body weight over a larger surface area, preventing them from sinking into soft ground. Ornithischian dinosaurs, a diverse group including the Stegosaurus and Triceratops, displayed yet another unique range of foot types. Many possessed 4 or 5 weight-bearing toes, with some species even evolving hoof-like structures on their toes. This particular adaptation was especially beneficial for traversing varied and uneven terrain, and for efficiently supporting their often bulky bodies. Some dinosaurs even developed highly specialized foot structures for very specific purposes. The dromaeosaurs, close evolutionary relatives of birds, were characterized by a distinctive sickle-shaped claw prominently featured on their second toe, which they could retract and hold off the ground while walking. This unique feature likely aided them in both hunting and climbing, powerfully showcasing how foot structure could evolve for highly specialized functions within different dinosaur lineages. The incredible variety in dinosaur foot architecture is a profound testament to the power of natural selection. Biomechanics, the study of the mechanics of living organisms, has absolutely revolutionized our understanding of dinosaur movement. This cutting-edge field has shed profound
profound new light on how these ancient creatures walked, ran, and interacted with their environment. By meticulously analyzing fossilized bones and their associated trackways, and utilizing advanced computer modeling techniques, scientists have unearthed fascinating insights into dinosaur locomotion that were previously unimaginable. One pivotal discovery, stemming from rigorous biomechanical analysis, is that many of the largest dinosaurs, such as the formidable Tyrannosaurus rex, likely moved at a considerably slower pace than had been widely depicted in popular culture. Contrary to the thrilling but often exaggerated cinematic portrayals in movies, these massive predators probably had a top speed closer to around 12 miles per hour. This more realistic finding is based on detailed studies of muscle attachment points on their bones, the inherent strength of their skeletal structures, and a comprehensive understanding of the creature's overall body mass. Researchers also surprisingly revealed that some dinosaurs, particularly the long-necked sauropods, may have been far more agile than their sheer size would suggest. Sophisticated computer simulations have convincingly demonstrated that despite their enormous bulk, these colossal giants could potentially have reared up onto their hind legs to access high-lying vegetation or to defend themselves from perceived threats. This groundbreaking insight profoundly challenges the long-held, older notion of sauropods as merely lumbering, slow-moving animals. Furthermore, the biomechanical analysis of dinosaur tails has provided crucial insights into their role in balance and propulsion. Many theropod dinosaurs, like the agile velociraptor, ingeniously used their muscular tails as vital counterbalances when running, allowing for incredibly quick turns and agile dynamic movements. This newfound understanding has fundamentally reshaped our view of how these formidable predators hunted and how they engaged with their prey, painting a far more complex and scientifically accurate picture of their dynamic existence. Dinosaur vision has always been a captivating subject for both paleontologists and evolutionary biologists. Through careful and detailed examination of fossil evidence, combined with insightful comparisons to modern animals, scientists have painstakingly pieced together intriguing insights into how these ancient creatures perceived their world. Many dinosaurs, particularly the predatory species, likely possessed excellent vision. Skull fossils often reveal remarkably large eye sockets, which strongly suggest that they housed big light-gathering eyes. This would have been absolutely crucial for hunting, especially for those species that may have been active during dawn, dusk, or even throughout the night. Some scientists even believe that certain dinosaurs, such as the formidable Tyrannosaurus rex, might have possessed vision as sharp and acute as that of modern-day hawks or eagles. Color vision was most probably a common feature for many dinosaurs, particularly among the smaller, more bird-like species. This conclusion is largely based on the discovery of specific eye structures found in exceptionally well-preserved fossils. Color vision would have conferred significant advantages, aiding in the identification of potential mates, the recognition of different species, and the crucial spotting of colorful fruits or flowers for herbivorous dinosaurs. Interestingly, some dinosaurs may have also exhibited enhanced depth perception due to the precise positioning of their eyes. Predatory dinosaurs often had forward-facing eyes, providing them with binocular vision, a trait similar to modern predators. This arrangement allows for far better judgment of distances, which would have been absolutely critical when launching into a chase after prey or navigating through dense or complex environments. The nuances of dinosaur vision continue to be a fascinating area of ongoing research. The hearing capabilities of dinosaurs were quite distinct from those of many modern animals, elegantly reflecting their unique evolutionary paths and the specific environments they inhabited. By meticulously studying their fossilized skulls and the delicate inner ear structures preserved within, scientists have gained invaluable insights into how these ancient creatures perceived sound. Many dinosaurs, especially the larger species like the colossal Tyrannosaurus rex, possessed hearing ranges that were primarily focused on low-frequency sounds. This specific adaptation would have allowed them to detect the ponderous footsteps and deep vocalizations of other large dinosaurs from considerable distances, providing a crucial early warning system, or aiding in tracking. In intriguing contrast, most mammals today, including humans, possess a much broader range of hearing that encompasses higher frequencies. Interestingly, some dinosaurs, particularly the smaller species and those closely related to modern birds, developed more sophisticated hearing abilities. These creatures could likely detect a wider spectrum of frequencies, quite similar to contemporary birds. This enhanced hearing would have been vitally important for complex communication within their species, for the crucial detection of predators in their vicinity, and for efficiently locating prey within dense forest environments. Comparing dinosaur hearing to that of their closest living relatives, crocodiles and birds, provides further illuminating insights. Crocodiles, much like many dinosaurs, are highly sensitive to low-frequency sounds, while birds have evolved the capacity to hear a broader range, including higher frequencies. This suggests that dinosaur hearing likely spanned a continuum between these two extremes, with precise variations evident across different species and families, reflecting their specific ecological needs and adaptive pressures. The study of ancient hearing offers a profound echo from the Mesozoic. Paleontologists have unearthed truly fascinating evidence regarding the olfactory abilities of dinosaurs through careful and systematic study of their fossilized skulls. By meticulously examining the dimensions and morphology of the olfactory bulbs and the intricacies of the nasal cavities in various dinosaur species, scientists have gained invaluable insights into the sophistication of their sense of smell. These olfactory bulbs, located in the front part of the brain, are the specialized regions responsible for processing scent information. One key piece of evidence comes from the discovery of exceptionally well-preserved skulls belonging to Tyrannosaurus rex. These fossils strikingly reveal that T. rex possessed proportionally large olfactory bulbs relative to its overall brain size, strongly suggesting an incredibly highly developed sense of smell. This potent olfactory capability likely played a crucial role in its hunting strategy, enabling T. rex to locate prey over considerable distances and potentially track scent trails with remarkable precision. Other dinosaur species also exhibit clear anatomical adaptations for enhanced olfaction. Herbivorous dinosaurs, such as the armored Stegosaurus and the horned Triceratops, had complex nasal passages that may have aided them in detecting predators or efficiently locating suitable food sources. Some scientists even propose that the elongated snouts of sauropods, like the majestic Brachiosaurus, could have housed intricate olfactory structures, potentially allowing these massive creatures to navigate their vast environments and pinpoint optimal vegetation. Recent advancements in cutting-edge imaging technology have empowered researchers to create highly detailed, three-dimensional models of dinosaur skulls, providing even more accurate assessments of their olfactory capabilities. These ongoing studies continue to refine our understanding of how different dinosaur species utilize their sense of smell to survive and thrive within their ancient ecosystems. The sense of smell was not merely a secondary sense but a vital tool for survival, adaptation and interaction in the Mesozoic world. Dinosaurs possessed truly beyond simply balance. Dinosaurs also heavily relied on proprioception, which is essentially their innate sense of body position and movement. Specialized receptors embedded within their muscles, tendons, and joints continuously provided constant, real-time feedback to their brains about the exact positioning of their limbs and the overall orientation of their bodies. This rich stream of internal information, combined with crucial visual cues from their surroundings, empowered dinosaurs to navigate their diverse environments with remarkable effectiveness and precision. Interestingly, some dinosaur lineages developed additional, even more specialized adaptations designed to enhance their spatial awareness. Certain species, like the duck-billed hadrosaurs, possessed noticeably enlarged optic lobes within their brains, strongly suggesting a highly developed visual acuity. This keen eyesight likely improved their ability to perceive depth with incredible accuracy and to judge distances with precision, further refining their spatial awareness as they moved through the complex and varied prehistoric landscapes. Whether it be dense forests or open plains, their ability to move with such grace and power, despite their often immense size, was a testament to these finely tuned sensory systems. Aquatic dinosaurs, a fascinating subset of these ancient giants, developed truly remarkable sensory adaptations that allowed them to not only survive but to thrive spectacularly within their watery environments. These specialized creatures, which included the graceful plesiosaurs and the streamlined ichthyosaurs, evolved unique features that enabled them to navigate, hunt, and endure beneath the waves of the ancient seas that once covered vast portions of our planet. One absolutely critical adaptation adaptation was their enhanced vision. Many aquatic dinosaurs possessed noticeably large eyes, often reinforced the brains of dinosaurs, while certainly different in scale and complexity from those of modern mammals. Much like those of modern reptiles and birds, possessed specialized regions meticulously dedicated to processing different types of sensory information. The olfactory bulbs, the specific areas of the brain primarily responsible for processing the sense of smell, were often notably well developed in many dinosaur species. This anatomical observation strongly suggests that a keen sense of smell was paramount for their survival and daily activities. This was particularly true for formidable predators like Tyrannosaurus rex, which likely relied heavily on its powerful sense of smell to efficiently locate both prey and potential mates across vast distances. The optic lobes, the brain regions dedicated to processing visual information, were also remarkably significant in many dinosaur species, especially within the highly visual predatory theropods. These enlarged optic lobes are a clear indication that vision played an absolutely crucial role in their daily lives, whether it was for the precision of hunting, the critical task of avoiding larger, more dangerous predators, or simply navigating their often complex environments. Some dinosaurs, such as the small bird-like Troodon, possess particularly large optic lobes, further suggesting incredibly highly developed visual capabilities. The cerebellum, the vital part of the brain primarily responsible for coordinating motor control and maintaining balance, was also notably well developed in many dinosaur species, especially in the swift bipedal theropods. This robust adaptation allowed for remarkably precise movements and intricate coordination, skills that were absolutely essential for both predators in pursuit and prey attempting evasion. An enlarged cerebellum in some species also hints at the potential for complex behaviors and possibly even sophisticated social interactions within their groups. While our detailed sense of touch played an undeniably crucial and multifaceted role in the lives of dinosaurs, serving as a vital conduit for interacting with their immediate environment and, perhaps more intimately, with each other. Dinosaurs, like virtually all living organisms, possessed an array of specialized touch receptors embedded within their skin. These receptors enabled them to perceive various physical stimuli, including direct contact, subtle changes in pressure, and fluctuations in temperature. These intricate sensory capabilities were absolutely essential for numerous aspects of their daily existence, ranging from basic navigation through complex terrains to intricate social interactions within their herds or family groups. For many dinosaur species, the sense of touch was particularly significant during their mating rituals and courtship behaviors. Some dinosaurs likely engaged in gentle nuzzling, or perhaps subtle rubbing against potential mates, as integral parts of their courtship displays behaviors that foster connection and acceptance. Additionally, touch was undeniably crucial for parental care in those species that actively nurtured their young. Fossil evidence, for example, strongly suggests that some dinosaurs, such as Maiasaura, meticulously cared for their offspring in communal nests, where tactile interaction would have been essential for feeding, protecting and comforting their vulnerable young. Dinosaurs also heavily relied on their sense of touch for the practicalities of foraging and feeding. Herbivorous dinosaurs, with their sensitive lips and tongues, would have used tactile feedback to distinguish between edible plants and potentially harmful vegetation, carefully selecting their sustenance. Carnivorous dinosaurs, on the other hand, likely utilized touch receptors in their snouts and around their powerful teeth to meticulously manipulate captured prey, ensuring the most efficient and effective way to consume their meals. Furthermore, the sense of touch played a substantial role in a dinosaur's ability to navigate their surroundings. Many species likely employed their tails, limbs, and other prominent body parts to physically feel their way through dense tangled vegetation or over challenging rocky terrain. This constant tactile feedback would have been especially invaluable in low-light conditions, such as twilight or dense forest undergrowth, or for those species with inherently limited vision, helping them to deftly avoid obstacles and accurately locate safe paths through their ancient habitats. The constant tactile connection to their world was a fundamental aspect of their daily survival. Nocturnal dinosaurs, those ancient creatures adapted to a life lived under the cloak of night, developed a suite of truly remarkable adaptations that allowed them to thrive in the profound darkness. Their eyes, a primary tool for navigating the night, evolved to become noticeably larger and exquisitely more sensitive, enabling them to gather even the faintest glimmer of light in dim conditions. The very shape of their eye sockets, as we can observe in fossilized skulls, expanded significantly to accommodate these enlarged, light-capturing eyes. These night-dwelling dinosaurs also evolved incredibly enhanced hearing abilities. Their internal ear structures became far more sophisticated, empowering them to detect the subtlest sounds of unseen prey or the approaching footsteps of predators in the inky blackness. Some species even developed asymmetrical ears, a fascinating adaptation where one ear was positioned slightly higher than the other. This subtle yet powerful arrangement helped them to pinpoint the exact location of sounds with astonishing accuracy, even in a three-dimensional space, providing a crucial advantage in the dark. The sense of smell became increasingly paramount for nocturnal dinosaurs. Their olfactory bulbs, the specialized parts of the brain responsible for processing scent information, grew proportionally larger over evolutionary time, indicating a heightened reliance on odor cues. This intensely developed sense of smell allowed them to efficiently track prey, locate hidden food sources, and meticulously navigate their environment using scent trails, particularly when visual information was severely limited. Touch sensors also played an absolutely crucial role in their nighttime adaptations. Many nocturnal dinosaurs developed exquisitely sensitive skin and specialized facial structures, some even possessing whisker-like sensory organs. These tactile adaptations would have helped them to carefully feel their way through dark, unfamiliar environments and to detect subtle air movements, offering an additional invaluable advantage in navigating and hunting under the profound cover of darkness. Their silent, effective mastery of the night was a testament to this suite of sensory refinements. The very size of dinosaur olfactory bulbs provides truly valuable and direct insights into the sophistication of their sense of smell. These specific brain structures, located prominently in the front part of the brain, are meticulously responsible for processing all incoming scent information. By carefully examining fossilized dinosaur skulls, paleontologists are able to estimate the precise size and intricate shape of these olfactory bulbs. This provides crucial clues about the relative importance of smell in the daily lives of different dinosaur species. Generally speaking, larger olfactory bulbs, especially when considered in proportion to the overall brain size, unequivocally indicate a more developed and acute sense of smell. Some predatory dinosaurs, most notably the fearsome Tyrannosaurus rex, possessed proportionally enormous olfactory bulbs. This strongly suggests that they relied very heavily on their sense of smell for their formidable hunting strategies and for navigating their complex environments. This enhanced olfactory capability likely allowed them to detect the presence of prey from considerable distances and potentially to precisely track scent trails with remarkable efficiency. In fascinating contrast, certain herbivorous dinosaurs, such as the armored Stegosaurus, exhibited comparatively smaller olfactory bulbs. This suggests that while their sense of smell was still present, it may have played a less critically important role in their day-to-day existence compared to vision or hearing. However, this does not imply that their sense of smell was entirely insignificant. Even with smaller olfactory bulbs, these dinosaurs might have effectively used scent cues to identify suitable food sources, perhaps distinguishing between different plant types, or to detect the subtle lingering presence of predators in their vicinity. Meticulously studying the variation in olfactory bulb size across a diverse array of different dinosaur species helps scientists to profoundly understand how these ancient creatures interacted with their environments and with each other. This invaluable information contributes significantly to our broader comprehension of dinosaur behavior, their ecological roles, and their long-term evolution, ultimately painting a far more complete and nuanced picture of life during the vast and ancient Mesozoic era. Dinosaurs, much like all complex living creatures, developed increasingly sophisticated sensory abilities. Hearing abilities also advanced considerably within the dinosaurian lineage. Over time, dinosaurs gradually evolved more complex internal ear structures, which allowed them to detect a broader range of frequencies and to pinpoint the exact direction of sounds with greater accuracy. This significant improvement in auditory perception was particularly crucial for both predators, helping them to locate their next meal and
Their
prey,
immense longevity
providing vital
meant they
early
experienced
warnings,
countless
thereby
seasonal
enhancing
cycles,
their survival
undertook
skills
numerous
within
immense
diverse
migrations
and
across
complex
continents,
ecosystems.
endured many
The
gradual,
sense of
subtle
smell
changes in
became
their ancient
increasingly
world,
important
and
for many
accumulated a
dinosaur
vast silent
species.
biological
The
history within their
olfactory
very
bulbs
bones.
within their
Each
brains grew
microscopic layer a
progressively
chronicle of
larger
time and a
over time,
testament to their enduring
clearly
presence.
indicating a greater
Further
reliance on
regulation,
scent for fundamental
precise and
activities
critical
such as finding
physiological
food,
process by
detecting
which an
imminent
animal
danger,
actively
and even
maintains
for
a
intricate
stable
communication
core
with
body
other
temperature
members of their
despite
species.
external
Some
fluctuations
highly
was
specialized
an immense and
dinosaurs, such as
ever-present
the
challenge for
distinctive duck-billed
dinosaurs,
hadrosaurs,
especially for
developed
their
elaborate
truly immense
nasal
forms.
passages.
Even
These
if not
anatomical
fully warm-blooded
complexities
in the
may have
modern
not
sense
only
of a
enhanced
bird
their
or
sense
mammal,
of smell,
capable
but
of
potentially
constant
served
high-level
other,
internal heat
dinosaurs.
generation.
These
Sheer
ancient
size
monumental
played a crucial
beings that
and
once
fascinating
strode across
role
the
in what is
earth
known as
were not,
gigantothermy.
despite their
This
imposing
principle
size
dictates
and
that very
formidable
large
appearance,
animals, by virtue
immune
of
to
their
the
immense
myriad
volume
afflictions
relative
and
to their
challenges that
comparatively
inevitably
smaller
confront
surface
all
area,
living
lose
organisms.
heat
Their
incredibly
fossilized
slowly to their
remains,
surroundings.
carefully
This is due
unearthed
to
from
the
the deep
physics of heat
geological
transfer.
archives of
The
our
larger the
planet,
body, the less
often bear the
surface area there
poignant
is per
silent
unit of
testimony
volume
of
to
the health
radiate heat
struggles and
away.
physical
The colossal
hardships that these
sauropod,
magnificent
once warmed
reptiles
by its
endured
internal
throughout their
metabolism
vast
or by
reign.
the sun radiant energy,
Paleontologists,
would take an
acting with the
incredibly long
meticulous
time to
precision
cool
of
down,
seasoned medical
essentially
examiners
acting as
from
a
an
giant
unimaginable
living thermal
past,
battery,
have patiently and
maintaining a
diligently
relatively
uncovered
stable
compelling
warm
evidence
core
of
body
various
temperature,
common and
almost
sometimes
regardless of
quite severe
significant
health
external
issues that
temperature
profoundly
fluctuations.
impacted dinosaur
Hypothetical
populations.
calculations
One
and
particularly
complex thermal
prevalent and
models
often debilitating
simulating heat
condition observed
exchange
was
in vast
arthritis,
reptilian
a
bodies
degenerative
suggest
joint
that a
disease.
sauropod
The
internal
telltale
temperature might
signs
have
of this
varied by
ailment
only
are
2 to
starkly
3
etched
degrees
into their
Celsius
fossilized
over a
bones,
24-hour
much like the
cycle.
rings of a
Even
tree
with
reveal its
significant
history.
external temperature
Researchers
swings of
have, for
perhaps 10
instance,
to 15
discovered
degrees
dinosaur
between day
vertebrae,
and night.
the very
A
building
remarkable
blocks
feat
of their
of passive
colossal
thermal
spines that
stability
were
achieved
unnaturally and
simply by
painfully
being so
fused
enormous.
together.
Beyond
This
the passive
ossification
effects
is a
of
clear and
gigantothermy,
undeniable
which
indicator of
primarily
severe
applied to
chronic
the largest
cases of
forms,
spinal arthritis,
behavioral
a
strategies
condition
were
that would have undoubtedly
crucial for all
inflicted immense
dinosaurs
and
to
persistent
actively
pain
manage
upon
their
the
heat.
affected
This
individual.
included
Such a
dedicated
disability
basking in
would
the
have
sun to
significantly
absorb heat
limited their
efficiently in
agility and
cool
overall
mornings,
mobility,
accelerating their
profoundly
internal warming
impacting their
processes,
fundamental
or
ability to
conversely,
hunt for
seeking
sustenance,
deep concealing
to
shade
efficiently
under the
forage for
largest
vital
trees,
plant
or
resources,
wading into
or,
ancient
most
lakes and rivers
critically,
during the
to
hottest
swiftly
parts of
escape
the
from
day
the
to
ever-present,
dissipate excess heat
terrifying
through
threat of
evaporative
larger,
cooling
more
from their
agile
skin,
predators
and
that
direct
lurked in
heat
their
transfer to the
primordial
water,
world.
using their
Imagine,
vast
if you
body
will,
surfaces.
the ceaseless
Anatomical
gnawing ache that would
features
have
also played a
permeated the
subtle
immense body
but
of such
highly
a colossal
significant
animal,
role in their
its
active
once graceful
thermoregulation.
movements now
The
hampered,
large
its
sails of
powerful strides
Spinosaurus,
reduced to
or
a
the prominent
laborious
plates of
shuffle,
Stegosaurus,
unable to
might
evade
have been
danger
highly
or secure its
vascularized,
next meal with
filled
its
with
former
intricate
prowess.
networks of blood vessels just beneath
Infections,
the
both
skin,
internal
allowing them
and
to act as
external,
efficient heat
represented
radiators or
another
solar
highly
collectors,
significant and
absorbing or
pervasive
dissipating
health
warmth as
concern
needed,
for
much like the
dinosaurs,
large blood-rich
posing a
ears of an
constant
elephant used for
insidious
cooling,
threat to
or
their
the fin
very
of a
survival
swordfish.
in a world
For
utterly
instance, the
devoid of even the
hypothetical
most
vascular network
rudimentary
within a
medical
Stegosaurus
intervention.
plate could have
The
increased
fossil
heat
record,
dissipation by
through
10
its
to
rare and
15%
precious
through
windows into the
convection and
past,
radiation,
provides poignant and
significantly aiding
often
in
grim
cooling a
evidence
massive
of
body during peak heat
osteomyelitis,
exposure,
a
preventing
severe and
overheating.
intensely painful
Feathers,
type
as
of
we
bone
explored in the
infection.
previous section,
This condition
provided
could lead
critical
to
insulation,
extensive
trapping
inflammation,
a layer of warm air close to
excruciating
the body,
pain,
crucial
and
for smaller,
noticeable,
more
often
active feathered
grotesque
dinosaurs to
deformities
maintain a
within
high
the very
stable body
structure of the
temperature
bone
in
itself.
varied and
This
fluctuating climates,
debilitating infection
reducing their
likely
reliance
stemmed
on
from
external heat
traumatic
sources
injuries
and
or
allowing
open
for
wounds
sustained
sustained
activity
during
across a
fierce,
wider range of
desperate
ambient
hunts,
temperatures,
violent
even venturing into
territorial
cooler
battles,
regions.
or
This
even
intricate
unforeseen
combination of
accidental
immense size,
falls,
intelligent
all of
behavior,
which
and
provided
specialized
entry
anatomy
points for
allowed
pervasive
dinosaurs to
bacteria
flourish in
present in
diverse
the
global
ancient
climates,
environment.
from tropical
Such
jungles to
untreated
even temperate
infections
polar
could
forests.
potentially lead to
The
prolonged,
cardiovascular
agonizing health
system of
problems,
dinosaurs,
chronic suffering that
especially
would
in the
linger for
largest
years,
sauropods,
slowly
must have
eroding
been
the
an
dinosaur's
incredibly
strength,
powerful and
or
highly
tragically
efficient
culminating in the
biological
eventual
machine,
death of
a
the
testament
affected
to
dinosaur,
evolutionary
succumbing not
engineering
to
on
the
a grand
direct, swift
scale,
strike of a
designed to
predator's
pump
claw,
immense
but to an
volumes of blood
unseen,
against the
relentless enemy
formidable
festering
force of
within its own
gravity to
formidable
reach
body.
immense heights.
Furthermore, the
Consider
insidious
the
presence of
extraordinary
parasitic
physiological
infestations populations also deeply troubled these ancient giants, much as internal parasites continue to afflict modern wildlife populations today. Tiny yet remarkably distinct boreholes and lesions found in some fossilized bones, for instance, strongly suggest the presence of internal parasites that burrowed directly into the dinosaur's skeletal framework, causing chronic irritation, slowly undermining their structural integrity and making them far more susceptible to other debilitating diseases or to the ever-present watchful threat of predation from other larger, more formidable animals. Additionally, scientists have made intriguing and truly invaluable discoveries of fossilized species known scientifically as coprolites, which under careful microscopic analysis have been found to contain the minute yet unmistakable eggs and even the fossilized casings of various intestinal parasites. These microscopic revelations unequivocally indicate that dinosaurs, from the smallest to the largest, suffered from a wide spectrum of internal parasitic infestations as well, a testament to the timeless and universal struggle against unseen microbial and invertebrate foes that predate even the dinosaurs themselves. Even the terrifying, omnipresent spectre of cancer, though admittedly rare in the fossil record due to the inherent difficulties of soft tissue preservation over millions of years, has been unequivocally identified in some dinosaur remains. A notable and profoundly impactful example is a confirmed case of osteosarcoma, an aggressive and often fatal type of bone cancer, painstakingly identified in a Centrosaurus fossil, a creature renowned for its formidable neck frill and iconic horns. This chilling discovery powerfully suggests that even these mighty, seemingly invincible creatures, towering symbols of primeval strength and biological prowess, were not immune to the fundamental cellular mutations and uncontrolled growths that can ultimately lead to cancerous afflictions, highlighting a shared biological vulnerability that transcends vast stretches of evolutionary time and deeply connects ancient life to our own fragile existence. While our comprehensive and detailed understanding of dinosaur diseases remains inherently limited by the very nature of fossil evidence available, often providing only tantalizing fragments, these extraordinary findings provide truly fascinating and often poignant insights into the complex and unremitting health challenges faced by these magnificent prehistoric animals, starkly reminding us of their deep biological reality and the common struggles of life across eons, a shared thread through deep time.
Paleontologists, driven by an insatiable curiosity to unravel the intricate tapestry of ancient life, employ a highly specialized and meticulously refined set of techniques to accurately identify injuries in dinosaur fossils, a demanding process that skillfully combines sharp, discerning observation with the transformative power of advanced modern technology. One fundamental and critically important method involves an incredibly close and painstaking examination of the bones themselves, searching for any subtle yet telltale signs of abnormal growth, clear and distinct breaks, or unusual patterns that deviate from healthy bone structure. Healed fractures, for example, often leave distinctive marks, thickened calluses of new bone, or even noticeable, permanent deformities on bones, providing undeniable evidence of where a traumatic injury occurred and, crucially, how the bone remarkably mended over time. These visible signs serve as a powerful testament to the animal's resilience and its inherent capacity for biological recovery. Such evidence directly indicates that the dinosaur not only survived the initial trauma, but continued to live, perhaps enduring chronic pain for a significant period afterward, engaging in its daily struggles for survival. The advent of computed tomography, CT scanning, a revolutionary technology now commonplace in medical diagnostics and colloquially known simply as CT scanning, has profoundly transformed and vastly enhanced the study of dinosaur injuries. This non-invasive and incredibly powerful technology allows scientists to peer deep inside fossilized bones with astonishing clarity and resolution, much like advanced X-ray vision, but with far greater detail and three-dimensional insight, all without causing any damage whatsoever to the invaluable and irreplaceable specimens. It reveals intricate internal structures and precise details of potential trauma or disease that would otherwise remain completely hidden and utterly inaccessible to the naked eye. By creating incredibly detailed, high-resolution three-dimensional images, researchers can identify even the most subtle changes in bone density or minute structural irregularities that might strongly indicate past injuries, whether they were acute, sudden traumas from a violent clash, or chronic, long-term conditions that slowly eroded bone health. These sophisticated scans can sometimes even reveal the intricate internal healing process, showing how new bone tissue was painstakingly laid down to repair the damage, layer by microscopic layer over time. Comparisons with modern animals also play an absolutely crucial and highly illuminating role in understanding the nature of dinosaur injuries and pathologies. By diligently studying similar conditions, observing disease progressions, and analyzing healing processes in living reptiles and birds, who are the closest living relatives of dinosaurs and share deep ancient evolutionary roots, paleontologists can make highly informed and scientifically sound inferences about the types of diseases and traumatic injuries that likely affected their ancient
counterparts. This comparative anatomical and physiological approach is absolutely essential. It helps bridge the immense chronological gap between the distant primeval past and our current evolving understanding of animal health and disease, providing a vital framework for accurate interpretation. Furthermore, microscopic analysis of bone tissue, a discipline known as bone histology, provides yet another invaluable and highly detailed tool for identifying injuries. By examining incredibly thin, almost translucent sections of fossilized bone under a powerful, high-magnification microscope, researchers can detect minute changes in bone cell structure and the microscopic patterns of growth that may definitively indicate past trauma or the lingering effects of disease. This extraordinary level of detail allows scientists to painstakingly piece together a far more complete and nuanced picture of an individual dinosaur's unique life history, including not only the specific injuries it courageously survived, but also how those injuries might have potentially affected its daily behavior, its ability to move and hunt effectively, and ultimately its long-term survival in a harsh, unforgiving prehistoric world. This microscopic detective work, delving into the very cellular architecture of ancient bones, brings the personal struggles and triumphs of ancient lives into astonishingly sharper, more empathetic focus. The fossil record, a silent yet incredibly eloquent chronicle embedded deep within the Earth's very crust, provides truly fascinating and often moving insights into the remarkable healing and recovery capabilities of dinosaurs. Paleontologists, through their relentless dedication to excavation and meticulous patient study, have uncovered numerous compelling examples of healed injuries in dinosaur bones, offering a profound glimpse into the inherent resilience and sheer tenacity of these ancient creatures in the face of adversity and severe physical trauma. One particularly notable and globally recognized case is that of an Allosaurus, a large, formidable carnivorous dinosaur that roamed the Earth during the late Jurassic period. Its fossilized remains clearly and unmistakably show a rib that had been definitively broken, shattered in some ancient violent struggle or accidental fall, and subsequently healed. This undeniable evidence unequivocally indicates that the animal survived a significant debilitating injury and lived long enough for the bone to mend completely, a powerful testament to its formidable recuperative powers and its sheer indomitable will to survive in a brutal and unforgiving ecosystem. This particular Allosaurus likely experienced discomfort, but its body's natural healing mechanisms were robust enough to allow it to continue its existence. Another remarkable and globally recognized piece of evidence comes from Sue, the legendary Tyrannosaurus rex specimen, widely regarded as one of the most complete and extensively studied T-Rex skeletons ever found. This famous fossil displays several clearly healed injuries, including a noticeably damaged shoulder blade and ribs that had mended after being severely broken, perhaps from a powerful impact, a struggle with immense prey, or a clash with a rival T-Rex. These compelling findings strongly suggest that even apex predators perched at the very pinnacle of the food chain could make astonishing recoveries from severe, potentially life-threatening wounds, and against all odds continue to thrive and dominate in their harsh and unforgiving ancient environments. Imagine the sheer determination and powerful drive for survival of such a creature, continuing its relentless hunt despite lingering pain or potentially reduced mobility. Herbivorous dinosaurs, despite their often more placid diets and generally less overtly aggressive lifestyles, also present compelling evidence of healing from significant trauma. Fossils of Triceratops, the iconic three-horned dinosaur, have been discovered with definitively healed fractures in their distinctive and massive frilled skulls. These injuries likely stemmed from intense intra-species combat, perhaps violent territorial disputes, brutal clashes over mates, or dominance displays within their herds, strikingly similar to how modern horned animals engage in fierce head-to-head battles today. The undeniable fact that these severe cranial wounds healed clearly indicates that individual Triceratops could survive and recover from even the most intense physical confrontations with their own kind, showcasing their remarkable durability and the surprising effectiveness of their frills as both defensive shields and tools in ritualized combat. Perhaps most intriguingly,
Some dinosaur fossils even display visible signs of chronic diseases that the dinosaurs lived with for extended periods, enduring suffering that never quite fully resolved. For instance, certain hadrosaur vertebrae, the individual bones of their spinal column, exhibit clear and unmistakable evidence of a condition strikingly similar to modern-day arthritis. The bones show the classic signs of this chronic ailment: inflammation, degeneration, and structural changes, yet the animal demonstrably survived long enough for these pathological changes to become clearly visible and permanently preserved in its fossilized remains. This powerful evidence highlights the astonishing ability of dinosaurs to adapt and persist despite ongoing health challenges, enduring discomfort, pain, or disability for considerable lengths of time within their ancient world, a testament to the resilience of life itself. Each healed bone, each subtle abnormality, tells a silent, profound story of survival, resilience, and the relentless struggle for existence against the backdrop of millions of years, bringing the individual, often arduous, lives of these ancient giants into sharper, more poignant and deeply empathetic focus.
Parasites, those ubiquitous and often unseen biological companions, played a significant, often unappreciated, yet undeniably crucial role in shaping dinosaur populations, much as they continue to profoundly influence animal communities across the globe today. These ancient creatures were by no means immune to the insidious and pervasive effects of parasitic organisms, which spanned a vast biological spectrum, from microscopic, single-celled pathogens to larger, more macroscopic parasitic worms. The fossil record, through incredibly rare yet invaluable discoveries, has yielded tantalizing traces of parasitic infections within dinosaur remains, offering profound and intimate insights into the complex and often brutal ecological relationships that defined the Mesozoic era. One particularly notable and illuminating example comes from fossilized dinosaur feces, or coprolites, which under careful microscopic scrutiny in modern laboratories have been found to contain the minute, yet unmistakable eggs, and even the fossilized casings of various parasitic worms. These minuscule, yet incredibly informative clues paint a vivid and somewhat unsettling picture of the complex internal ecosystems that existed within dinosaur bodies, hidden from external view. Researchers have, for instance, identified the distinct eggs of ancient relatives of tapeworms, tiny flukes, and various roundworms, some of which, remarkably, still plague modern animals today, a testament to the longevity and persistent evolutionary success of these biological interactions. The meticulous study of coprolites has unequivocally revealed that some dinosaurs suffered from parasitic infections remarkably similar to those found in contemporary wildlife. For instance, scientists have identified pinworm eggs embedded within tyrannosaur coprolites, strongly suggesting that these fearsome apex predators, despite their imposing might, were surprisingly not immune to intestinal discomfort and the debilitating effects of such widespread infestations. Such findings help us to intimately understand the range of health challenges dinosaurs faced and, crucially, how parasites themselves have co-evolved and adapted alongside their hosts over countless millions of years, locked in a timeless, relentless evolutionary arms race, each side constantly adapting to the other. Moreover, coprolite analysis extends its reach far beyond individual dinosaur health, offering a unique temporal window into broader ecological and evolutionary questions. By comparing parasites found in dinosaur coprolites from different time periods and geographical locations, researchers can meticulously track changes in dinosaur diets and the overall health of their ancient ecosystems over immense stretches of geological time. This long-term, deep perspective offers crucial insights into how dinosaurs adapted to constantly changing environments, and how their roles within ancient ecosystems evolved throughout the entirety of the Mesozoic era, showcasing the intricate and often harsh realities of ancient life, where even the mightiest fell prey to the smallest. Scientists delve into the specialized and increasingly sophisticated field of paleopathology of dinosaurs through a meticulous and highly precise examination of fossilized bones and other exceptionally preserved remains. This fascinating and intricate discipline effectively combines the rigorous methods
methodologies and deep knowledge of paleontology with the insights of modern medical science, allowing researchers to understand the specific diseases, traumatic injuries, and broader health conditions that profoundly affected these ancient creatures millions of years ago. One fundamental and critically important method involves the close and painstaking analysis of bone abnormalities. Researchers carefully search for any subtle yet undeniable signs of fractures, conclusive evidence of past infections that have left their mark on the bone, or the disconcerting presence of tumors within fossilized dinosaur bones. These abnormalities, much like the scars and histories etched onto human medical records, can unlock a wealth of information about the daily challenges dinosaurs encountered in their often harsh environments, and how they remarkably coped with traumatic injuries or chronic debilitating illnesses. For example, the presence of clearly healed fractures where the bone has reformed around a break, might indicate that a dinosaur courageously survived a severe traumatic injury, powerfully demonstrating their inherent resilience and remarkable ability for biological recovery, even when faced with significant physical damage. Conversely, the identification of unhealed breaks might suggest fatal injuries or provide crucial clues about the precise circumstances of the dinosaur's death, painting a picture of its final moments. Furthermore, clear evidence of bone cancer or other forms of neoplastic growth could shed invaluable light on the specific types of cellular diseases and genetic predispositions that afflicted these prehistoric animals, showing that even deep time cannot escape certain fundamental biological realities of life and disease. Advanced imaging techniques play an absolutely crucial and transformative role in this specialized research, pushing the very boundaries of what is scientifically possible in paleontology. Computed tomography CT scans, for instance, a staple in modern medicine, enable scientists to peer deep inside fossilized bones with astonishing clarity and resolution, all without causing any damage whatsoever to the invaluable and irreplaceable specimens. This non-destructive approach provides unprecedented insights into the intricate internal structures of bones, revealing hidden abnormalities or pathologies that might not be visible on the external surface. These highly detailed, three-dimensional scans can help identify subtle areas of abnormal bone growth, pinpoint regions of bone density loss, or discern intricate patterns of decay, providing vital clues about the health status and the unique life experiences of individual dinosaurs. Beyond individual cases, such scans can reveal broader population-wide health trends, indicating common ailments or injuries within a species. And furthermore, comparisons with modern animals are incredibly informative and form a cornerstone for understanding dinosaur paleopathology. By diligently studying similar conditions, observing disease progressions, and analyzing healing processes in living reptiles and birds, who are the closest living relatives of dinosaurs and share deep ancient evolutionary roots, paleontologists can make highly informed and scientifically sound inferences about the diseases and injuries that likely affected their ancient counterparts. This comparative anatomical and physiological approach is absolutely essential. It helps bridge the immense chronological gap between the distant, primeval past and our current evolving understanding of animal health and disease, providing a vital and robust framework for accurate interpretation. Recent advancements in this field are continually pushing the boundaries of what we can learn from these ancient medical mysteries, allowing us to empathize with the struggles and triumphs of creatures long gone, reminding us that biological challenges are as old as life itself. Recent and truly groundbreaking dinosaur discoveries have profoundly revolutionized our understanding of these ancient creatures, dramatically reshaping our perceptions of their lives, their diverse forms, and their monumental place in Earth's history. In the vast, remote, and fossil-rich landscapes of Argentina, paleontologists made an astonishing and awe-inspiring find, unearthing the colossal fossils of a new species of titanosaur, a creature of such immense scale that it may well represent the largest land animal to ever grace the Earth. This magnificent herbivore, formerly named Patagotitan murorum, stretched to an incredible length of over 120 feet, making it longer than many modern jumbo jets,
and weighed as much as a staggering 70 tons, a truly incomprehensible mass that easily dwarfed all other known terrestrial giants. This particular discovery continues to provide vital data on the phenomenon of sauropod gigantism and the biological limits of terrestrial size. Another incredibly exciting and remarkably rare find emerged from ancient amber deposits in Myanmar, where scientists discovered the perfectly preserved tail feathers of a small carnivorous dinosaur. This remarkable specimen, a tiny fragment of a creature trapped in hardened tree resin for millions upon millions of years, provides direct, undeniable and stunning evidence of feathered dinosaurs. This finding unequivocally confirms a theory that had long been debated within scientific circles, and it offers invaluable tangible insights into the intricate and beautiful evolution of birds directly from their dinosaurian ancestors. The preservation is so exquisitely detailed that even the microscopic microstructure of the feathers can be studied, revealing their precise form and function. In China, researchers uncovered a precious nest of dinosaur eggs containing exquisitely preserved embryos inside. This unprecedented discovery provided an unparalleled, intimate and never-before-seen look at the very earliest stages of dinosaur development. These fossilized embryos belong to a species of long-necked dinosaur, precisely revealing how these colossal creatures grew and developed within the protective confines of their eggs before hatching, shedding crucial light on their unique ontogeny, the course of their individual development. Lastly, a pivotal and somewhat controversial recent discovery in Morocco revealed the first definitively known aquatic dinosaur, Spinosaurus aegyptiacus. New fossil evidence, including surprisingly dense bones that would have aided in buoyancy control, and a powerful fin-like tail distinct in form from other large theropods, strongly indicates it was remarkably well adapted for a life spent primarily in the water, possibly hunting large fish or other aquatic animals with its crocodile-like jaws. These continuous groundbreaking findings collectively continue to dramatically reshape our image of dinosaurs, challenging long-held popular notions and highlighting their astonishing diversity and their unparalleled adaptations across nearly every conceivable ecological niche, from dry deserts to ancient seas. The story of these ancient titans, it becomes abundantly clear, is still very much being written, one incredible and often surprising discovery at a time, each new fossil adding another complex, fascinating and deeply profound layer to their magnificent and enduring saga. While the captivating prospect of extracting intact, viable DNA directly from dinosaur fossils remains a thrilling, yet currently elusive dream confined to the realm of science fiction, the broader field of DNA research has nonetheless profoundly revolutionized our understanding of dinosaurs. It has opened entirely new and unexpected avenues for exploring their intricate evolutionary history and their deep-seated biological relationships with other life forms, both ancient and modern. Although direct DNA recovery from fossils millions of years old faces immense scientific challenges due to the inherent instability and rapid degradation of the DNA molecule over such vast timescales, scientists have made significant and increasingly exciting progress by diligently studying the genetic material of living descendants and their closest biological relatives, by meticulously analyzing the DNA of modern birds who are now unequivocally considered the direct, living dinosaurs of our present day. Researchers have gained invaluable insights into the genetic makeup of their ancient avian ancestors. This indirect but powerful approach has been instrumental in clarifying the complex evolutionary connections between different dinosaur species, and has even allowed scientists to make highly educated and increasingly accurate guesses about certain dinosaur traits, such as their potential coloration, the intricate patterns of their feathering, and even aspects of their metabolic rates, painting a more vibrant biological picture of these long-extinct creatures. The molecular whispers of the past, though faint, are beginning to be deciphered and heard. Furthermore, DNA studies have shed crucial and compelling light on the catastrophic extinction event that tragically wiped out most non-avian dinosaurs,
approximately 66 million years ago. By examining the genetic diversity and population bottlenecks of surviving lineages, particularly mammals and birds, scientists have been able to estimate ancient population sizes and meticulously track how different groups of animals responded, both genetically and behaviorally, to the cataclysmic environmental changes that followed the asteroid impact. This work illuminates the selective pressures of mass extinction and provides insights into which traits allowed for survival. Recent advancements in molecular clock techniques, which ingeniously utilize known DNA mutation rates to estimate when specific species diverged from common ancestors, have also been instrumental in refining the complex and branching dinosaur family tree. This has led to a much better and more precise understanding of when specific dinosaur groups emerged, their periods of diversification, and how they subsequently spread across the globe, providing a robust timeline for their evolution. While DNA research by its very nature cannot yet provide a complete and fully detailed picture of dinosaur biology, its continuous evolution and application promise to be an invaluable and rapidly expanding tool in painstakingly piecing together the grand and ongoing puzzle of these fascinating creatures that commanded the Earth for over 160 million years, an unbroken lineage that continues to captivate and inspire future generations of scientists and enthusiasts alike. The invisible threads of genetic history still connect us to these ancient giants, bridging vast gulfs of time. Computer modeling has truly revolutionized dinosaur research, acting as a powerful digital microscope and a virtual time machine that allows paleontologists to explore intricate aspects of dinosaur biology and behavior that were previously utterly inaccessible through traditional physical methods. These advanced digital tools empower scientists to reconstruct extinct species with an unprecedented level of detail and remarkable accuracy, breathing digital life into ancient bones. One key and transformative application is in biomechanical analysis. Researchers utilize complex computer models to meticulously simulate how dinosaurs might have moved, testing various hypotheses about their potential speed, their remarkable agility, and their overall physical capabilities by inputting vast amounts of precise data derived from fossil remains, such as bone density, muscle attachment points, joint angles, and limb proportions, into these sophisticated models. Scientists can accurately estimate muscle strength, assess joint flexibility, and even simulate various dinosaur gaits, providing dynamic and visually compelling insights into their locomotion. This allows for rigorous testing of theories about how a T-Rex generated its powerful bite force, how a sauropod supported its massive weight without collapsing, or how feathered dinosaurs might have developed flight. Another crucial and foundational role of computer modeling lies in the comprehensive study of dinosaur anatomy. Three-dimensional scans of fossilized bones, obtained through CT scans or laser scanners, can be seamlessly converted into incredibly detailed digital models of dinosaur skeletons. These virtual models allow researchers to examine intricate internal structures with unparalleled clarity, precisely estimate overall body mass with greater accuracy than ever before, and even in some cases reconstruct soft tissues such as muscles, organs, and even the likely placement of fatty tissues and skin contours that very rarely fossilize. This technology has been particularly valuable in understanding the subtle, step-by-step evolutionary journey of avian dinosaurs into modern birds, visualizing the anatomical transformations that enabled the astonishing development of flight. Furthermore, computer simulations also assist paleontologists in understanding broader dinosaur ecosystems and complex behaviors by constructing detailed digital models of ancient environments, complete with their diverse flora and fauna, and then populating these virtual worlds with the various creatures that inhabited them. Researchers can test a wide array of theories about dinosaur social structures, their intricate hunting strategies, their resource partitioning, and their likely responses to significant environmental changes, such as shifts in climate, volcanic eruptions, or habitat availability. These immersive and interactive models provide an unparalleled digital window into the distant past, helping us to gain a much deeper and more nuanced understanding of the rich dynamics and often challenging lives of these fascinating creatures that majestically roamed the Earth millions of years ago. The ability to simulate and visualize
visualize these ancient worlds, to walk within them digitally and observe their inhabitants, is not just a technological feat, but a profound leap in scientific inquiry, bringing us closer to the magnificent, vibrant reality of these lost giants. The most widely accepted and scientifically robust explanation for the dramatic and swift extinction of the non-avian dinosaurs is known as the impact event hypothesis. This compelling theory posits that a truly immense asteroid, estimated to be approximately 10 kilometers, about 6 miles in diameter, a size comparable to Mount Everest, collided with Earth around 66 million years ago. The precise site of this cataclysmic collision, now famously identified as the Chicxulub crater, lies deeply buried beneath the Yucatan Peninsula in modern-day Mexico. When this colossal space rock hurtled through our planet's atmosphere and slammed into its surface, it unleashed an unimaginably catastrophic chain of events, an unleashing of energy equivalent to over 1 billion atomic bombs detonating simultaneously. The immediate force of the impact was so immense that it instantly vaporized vast quantities of rock and ejected an enormous amount of dust, ash, and superheated debris into the atmosphere, a colossal plume reaching far into space. This dense opaque material, suspended high above the planet, effectively blocked out sunlight for an extended terrifying period. The loss of solar radiation led to a rapid and severe global cooling, plunging the Earth into a prolonged impact winter. Plants, forming the very foundation of nearly all terrestrial food chains, were unable to photosynthesize effectively in these darkened, frigid conditions, leading to a catastrophic and widespread collapse of ecosystems across the globe. The initial impact also triggered a cascade of secondary disasters. Immense wildfires ignited across continents due to superheated debris raining down from the sky. Colossal tsunamis swept across coastlines, inundating vast landmasses, and powerful earthquakes shook the very bedrock of the planet. These interconnected events, combined with the prolonged darkness and profound cooling, created an utterly hostile and unlivable environment that the vast majority of large animals, including the mighty dinosaurs, simply could not survive. Only smaller, more adaptable creatures capable of finding shelter, surviving on minimal resources, or quickly adjusting to radically altered conditions, managed to endure these harsh post-impact conditions. The asteroid impact theory for the demise of the dinosaurs is not merely a hypothesis. It is supported by an impressive array of compelling and multidisciplinary lines of scientific evidence. The cornerstone of this theory is the remarkable and globally consistent discovery of a thin, distinctive layer of iridium-rich clay, found precisely at the geological boundary between the Cretaceous and Paleogene periods, often referred to as the KPG boundary, in rock formations across the entire planet. Iridium is an incredibly rare element on Earth's surface, but it is found in much higher concentrations in asteroids and other extraterrestrial objects, strongly suggesting an origin from outer space for this specific geological layer. Further bolstering this theory is the definitive identification of the Chicxulub crater on the Yucatan Peninsula in Mexico. This immense impact structure, measuring approximately 180 kilometers, about 112 miles in diameter, perfectly matches the estimated size and the precise age predicted by the impact theory. Meticulous studies of the crater have revealed distinct geological signatures, including the presence of shocked quartz and other unique minerals that only form under the extreme pressures and temperatures associated with a massive asteroid strike. The very architecture of the crater and the materials within it scream of an extraterrestrial impact. Fossil evidence further solidifies this theory. The global fossil record from this period unmistakably shows a sudden and widespread extinction of a vast multitude of species, precisely at the close of the Cretaceous period. This catastrophic event affected not only the non-avian dinosaurs, but also a significant percentage of marine reptiles, numerous plant species, and countless invertebrate groups. This abrupt and simultaneous change in global biodiversity aligns perfectly with the devastating and far-reaching effects expected from a major asteroid impact. Additionally, sophisticated computer models have been developed and rigorously tested, convincingly demonstrating how such a monumental impact could have initiated profound global climate changes. These models predict a prolonged period of darkness and severe cooling, triggered by the massive amounts of dust, ash, and aerosols ejected into the atmosphere. These grim conditions would have catastrophically disrupted photosynthesis, the very basis of most food chains, leading directly to the observed pattern of widespread extinctions across both land and sea. The combined weight of this geological, chemical, and biological evidence paints a clear and compelling picture of an asteroid impact as the primary driver of this monumental extinction event. While the asteroid impact is now widely accepted as the primary immediate cause of the dinosaurs' extinction, the extensive and prolonged Deccan Traps volcanism in what is now India played a significant, albeit often overshadowed role in preconditioning Earth's ecosystems for disaster. This colossal episode of volcanic activity commenced approximately 66 million years ago, precisely around the time of the asteroid impact, and continued for an astonishing nearly 1 million years. The sheer scale of the Deccan Traps eruption was immense, covering an area larger than modern-day France, with successive thick layers of basaltic lava, indicative of continuous massive outpourings from deep within the Earth's mantle. As these immense volcanoes relentlessly erupted, they spewed forth enormous quantities of greenhouse gases, primarily carbon dioxide, and critically, vast amounts of sulfur dioxide into the atmosphere. These gases had a profound and destabilizing effect on the global climate, leading to complex and unpredictable periods of intense global warming, followed by significant periods of cooling. This pervasive climate instability placed tremendous and unrelenting stress on ecosystems worldwide. Plants, the primary producers, struggled to adapt to the rapidly fluctuating conditions, which in turn severely impacted the herbivorous dinosaurs that depended on them for sustenance. The devastating knock-on effect then moved swiftly up the food chain, profoundly impacting carnivorous dinosaurs as well, as their prey populations dwindled. The massive influx of volcanic gases also led to widespread acid rain, which further damaged delicate plant life and, crucially, acidified the oceans, causing immense problems for marine life, particularly organisms with calcium carbonate shells. While the Deccan Traps eruption alone might not have been sufficient to trigger such a profound mass extinction, its long-term widespread environmental disruption demonstrably weakened ecosystems globally. This made life on Earth significantly more vulnerable and less resilient to the catastrophic asteroid impact that occurred around the same time, delivering the final fatal blow to the non-avian dinosaurs and countless other species across the planet. The grim synergy of these two major geological events created the perfect storm for a mass extinction, fundamentally reshaping the trajectory of life on our planet. While the asteroid impact is now almost universally accepted as the primary and most immediate cause of the dinosaurs' extinction, it is crucial to recognize that several other significant factors likely contributed to their demise, acting as insidious underlying pressures that weakened their populations. Climate change was already well underway before the asteroid impact, slowly but inexorably altering global conditions. Evidence suggests a gradual long-term cooling trend across the planet, accompanied by significant fluctuations in sea levels, with large areas of continental shelves becoming exposed. This gradual environmental shift was already altering established ecosystems, reducing the availability of certain habitats and putting increasing pressure on many dinosaur species, forcing them to adapt or face decline. As mentioned, the massive and prolonged volcanic eruptions in what is now India, known as the Deccan Traps, were also occurring concurrently with the late Cretaceous period. These immense eruptions released vast quantities of greenhouse gases and sulfur dioxide into the atmosphere, further disrupting global climate patterns and potentially poisoning both the air and water, creating a hostile atmosphere for many forms of life. The cumulative effect of these prolonged environmental stresses may have already weakened dinosaur populations, making them far more vulnerable and less resilient to the sudden catastrophic effects of the asteroid impact, which then delivered the final crushing blow. Some scientists proposed that dinosaurs were already experiencing a gradual decline in diversity and abundance due to these widespread environmental stresses, and the impact merely accelerated an already ongoing process of ecological change. Additionally, the rise of flowering plants, angiosperms, and the rapid evolution and diversification of new mammal species were subtly but profoundly changing the dynamics of ecosystems. Flowering plants introduced new food sources and competition for resources among plant eaters, while the increasing diversity of mammals may have brought new forms of competition or predation to the dinosaurian world. These
creating
nuanced
cascades
shifts in
of
vegetation and the
ecological change.
biological landscape
coevolution
may have
between
further
insects and
challenged the
angiosperms
dinosaurs'
was
ability to adapt
particularly
and survive in a
intense,
rapidly
with
changing
pollinators and
world,
herbivorous
ultimately
insects
contributing to their
diversifying
extinction
rapidly
alongside the more
alongside the
dramatic,
reflowering
singular
plants.
events of the
This
time.
burgeoning
It was
insect
likely a
diversity
complex
would then
interplay
in
of
turn
multiple
provide new
factors,
food sources for
culminating in a
smaller
perfect
insectivorous
storm of
dinosaurs and
disaster.
early
The
mammals,
epochal
adding
end of the
intricate layers to the
dinosaurs'
food
reign
web.
was
The
marked by a
sounds of buzzing
catastrophic and
insects, the
singular
subtle
event
fragrance of ancient
approximately
flowers,
66
and the rustling
million
of
years
leaves
ago,
underfoot would have
when a
been
massive
constant
asteroid
companions in the
slammed into
Cretaceous
Earth.
air.
This
The sensory
cataclysmic
scenery of
impact
the
triggered an
Mesozoic
immediate
was a
and
symphony
profound
of
cascade of
primeval
global
existence.
climate changes,
Imagine the
initiating a
pervasive,
period
earthy
of
smell
immense
damp
environmental
soil mixed with the
turmoil.
pungent,
The immediate
resinous aroma
aftermath
of
saw
vast
widespread
conifer
and
forests,
uncontrollable
occasionally
wildfires
punctuated by
raging
the
across
sweet and delicate
continents,
scents of
ignited
newly
by the
bloomed,
intense heat
simple
generated as
angiosperm
superheated
flowers.
debris
The
from the
sounds would have
impact
been a
rained
rich
back down
tapestry,
through the
the
atmosphere.
constant
The
low
very
hum and
air
buzz
filled
of
with thick
countless
choking
insects,
smoke and
some with
pulverized dust,
wingspans of a foot or
effectively
more,
blotting
the
out the sun
rustling of
and
ancient
plunging the
leathery
entire
leaves in the
planet into a
wind, the
prolonged
distant
period of
low thud
profound
a
darkness and
sauropod's
chilling
immense
cold.
footfall.
The
A
initial
vibration felt more
mind-numbingly
than
powerful
heard,
blast
the sharp
obliterated
snap of a
virtually all
theropod's
life
jaws
within
on prey,
hundreds of
and
miles
the
of the
booming
impact site,
low-frequency
leaving a
vocalizations
vast
of
scorched
hadrosaurs
wasteland.
resonating across
Powerful
vast
planet-wide
plains,
earthquakes
carrying for
violently
miles through
shook
the
the
humid
ground,
air.
triggering
Visually, the
immense
landscapes were
tsunamis that
often
swept across
dominated by
vast
shades of deep
coastlines,
green and earthy
inundating and
brown,
devastating
with vast
huge
open
areas of
skies,
land.
sometimes
Ominously,
shimmering
acid
with
rain
heat
fell
haze over
relentlessly
deserts.
from the
The very
skies,
texture of the
poisoning
air,
vital water
thick with
sources
moisture in
and
coastal
scorching the
regions or
delicate
dry and
vegetation
dusty
that had
inland,
somehow
would have
survived the
been
initial
palpable.
catastrophe.
Finally,
As the
within this
dust and
grand
debris slowly began to
dinosaur-dominated
settle
world,
from the upper
rich
atmosphere, a
biodiversity of
profound,
minor
eerie
fauna
silence
also
descended
thrived,
over much of the
finding
planet,
their own
where
ecological
once incredibly
niches,
diverse and vibrant
intricately weaving into
ecosystems
the
thrived
Mesozoic
with the bustling
tapestry.
sounds of life,
Amphibians,
now lay
including
barren,
ancient
lifeless
frogs and
wastelands,
salamanders,
scarred and desolate.
inhabited
The few
freshwater
surviving animals
environments.
faced a harsh
Numerous
new
species of
reality,
lizards and
struggling
snakes
desperately
slithered
to
through
find
the
what meager
undergrowth,
food and shelter
hunting
they could
insects
in a
and smaller
radically and
prey.
irrevocably
Early
altered
mammals,
world.
though
Plants
generally
withered
small
and died in the
nocturnal,
prolonged darkness,
scurried through the
utterly
shadows,
unable to
cautiously avoiding the
photosynthesize,
gaze of
leading to a
larger
widespread and
dinosaurs.
devastating
Crocodilians,
ecosystem collapse
often
that
much
rippled up
larger
every
and more
trophic
diverse
level.
than their
This
modern
period of
counterparts,
widespread
lurked in
devastation and
rivers and
ecological
swamps,
collapse lasted for
coexisting with
months,
freshwater
possibly even
turtles,
years,
insects
as Earth
from
slowly,
giant
painfully,
dragonflies to
began the
ancient
long
beetles
process
and
of
buzzing
recovery from the
hymenopterans,
cataclysm. The
flourished,
extinction event had
constantly
in essence
interacting with the
reset the
evolving
ecological
plant life
clock,
and
creating a
providing
vast
vital food
biological
source for
void and
smaller
paving the way
dinosaurs.
for new forms
These
of
less
life,
celebrated
particularly
creatures
mammals and birds,
formed
to
the intricate
emerge,
living background,
diversify and
the
adapt to
constant
the
hum of
fundamentally
life,
changed planet.
influencing and being
It unequivocally
influenced by
marked the end of the majestic
flora,
age of
and the
dinosaurs,
colossal,
and the dramatic,
magnificent
tumultuous
dinosaurs that
beginning
reigned
of a new
supreme.
chapter in
The
Earth's
Mesozoic
grand
was truly
unfolding
a
history.
complete and vibrant
The
world,
extinction of the
brimming with life in all
non-avian
its myriad
dinosaurs
ancient
marked an
forms.
undeniably
As the
pivotal
final
and
moments of
profound
the
moment in
Cretaceous
Earth's
period
long and
ebbed
complex
away,
history.
some
This
66
catastrophic
million years
event
ago,
effectively
the
cleared the
magnificent reign of the
ecological stage,
non-avian dinosaurs
setting the
came to an
perfect
utterly
conditions for the
abrupt
dramatic
and
rise and
cataclysmic
subsequent
end. This
diversification
profound
of
and
mammals,
pivotal moment in
triggered
Earth's
primarily
history,
by the
known as the
cataclysmic asteroid
Cretaceous
impact
Paleogene
approximately
PG
66
extinction
million
event,
years ago.
was triggered
This
by an
global
unimaginable
disaster
cosmic
tragically
collision.
wiped out
A
an
massive
estimated
asteroid,
75% of
estimated
all
to be
plant and animal
approximately 10
species on our
kilometers,
planet,
roughly
leaving a vast
6.2
void.
miles in
The sudden
diameter,
and
a
almost
size
complete
comparable to a
disappearance of the
significant
large
mountain,
dinosaurs, who
hurtled
had for
through
so
Earth's
long
atmosphere at
dominated every
extraordinary
major
speed,
terrestrial
perhaps
niche,
45,000
created an
miles per hour,
unprecedented number
and
of
violently
ecological
slammed into
niches
the
that were
planet.
suddenly
The
vacant
impact
and ripe
point,
for
now
exploitation.
identified as
In the
immense
immediate
Chicxulub
aftermath of
crater
this
buried
mass
beneath the
extinction,
Yucatan
mammals which
Peninsula
had
in
previously
Mexico
been
became
confined
the
to
epicenter
small,
of a
often
planetary
nocturnal and
catastrophe that
inconspicuous
unfolded with
roles in the
terrifying
shadow of their
swiftness
reptilian
and brutal
overlords,
intensity.
found themselves in
The
a world
immediate
with
aftermath
dramatically
was a
reduced
sequence of
competition
truly
and,
horrific
crucially,
and
an
devastating
abundance of
events.
previously
A chain
unavailable
reaction of
resources.
unimaginable
This newfound
destruction.
ecological
In the
freedom
seconds following
provided an
impact,
unparalleled
immense
opportunity
shockwave,
for rapid
traveling at
diversification
hypersonic
and
speeds,
explosive
pulverized
evolution
rock
of
and
mammalian
incinerated
species,
everything within a
freed from the
50-mile
constant
radius,
threat and competition of
creating an
large predatory
instantaneous
dinosaurs.
superheated
Mammals
inferno.
were now able
This
to
was
grow
followed in
larger,
minutes by a
explore
colossal
wider
tsunami,
geographical ranges and occupy far more diverse habitats. They evolved to fill an astonishing array of roles previously dominated by dinosaurs, transforming from small insectivores into large herbivores and eventually into formidable apex predators themselves. This period of intense adaptive radiation ultimately led to the development of the vast diversity of mammalian forms we see today, including our own primate ancestors. The extinction event also profoundly altered the terrestrial plant life on Earth, with flowering plants angiosperms becoming far more prevalent and ecologically dominant. This significant shift in vegetation provided new and varied food sources and habitats, further fueling the diversification of evolving mammals. Furthermore, the inherent mammalian ability to regulate their internal body temperature, warm-bloodedness, and to give birth to live young, providing internal incubation and direct parental care, proved to be significant evolutionary advantages in this rapidly changing and unpredictable world. These traits allowed them to thrive and ultimately dominate terrestrial ecosystems, ushering in the Cenozoic era, the age of mammals.
The sudden extinction theory, which posits that dinosaurs and many other species vanished abruptly and almost instantaneously due to a single catastrophic event, faces several nuanced and compelling challenges from scientific evidence. While the asteroid impact clearly represents a sudden massive shock to the Earth system, the fossil record from the late Cretaceous period preceding the impact indicates a more complex scenario. It reveals a gradual decline in dinosaur diversity over millions of years before their final disappearance. This slow, protracted decrease in species numbers and abundance suggests that dinosaurs were already struggling to adapt to changing environments and accumulating ecological pressures long before any sudden cataclysm. This decline, termed pre-impact decline, indicates an ecosystem already under stress. Additionally, meticulous studies of ancient plant fossils and pollen samples from this period indicate a gradual but significant shift in vegetation types leading up to the end of the Cretaceous. This profound change in plant life would have directly impacted herbivorous dinosaurs first, altering their primary food sources and potentially leading to nutritional stress, which in turn would have affected their carnivorous predators. Such a scenario supports a more drawn-out and complex extinction process, not merely an instantaneous die-off. Furthermore, detailed climate data, reconstructed from various geological proxies during this period, also points to long-term cooling trends and significant sea level changes that could have steadily stressed dinosaur populations over extended periods, weakening their resilience. These pervasive environmental shifts likely made some species more vulnerable to extinction, creating a domino effect rather than a single sudden event wiping them all out at once. It suggests a world already in flux, not a perfectly stable one. Perhaps most intriguingly, some dinosaur lineages appear to have persisted, albeit for a short time after the proposed impact event at the end of the Cretaceous. Fossils found in geological layers situated just above the telltale iridium-rich clay layer, which is universally associated with the impact, suggest that certain dinosaur species managed to survive for a brief period, perhaps decades, or even a few centuries, contradicting the idea of an instantaneous global extinction that spared no non-avian dinosaur. These lingering survivors, however, were likely too few and too dispersed to rebuild their populations in a drastically altered world. These accumulated scientific challenges advocate for a more nuanced understanding of the extinction, recognizing the immediate devastating impact, but also acknowledging the long-term environmental pressures that preceded it. Scientists continually refine our understanding of the dinosaur extinction event through a dynamic and evolving combination of advanced technologies and deeply interdisciplinary research. The very process of scientific inquiry is a relentless pursuit of greater clarity and precision. New geological evidence is constantly being uncovered through vastly improved drilling techniques, allowing researchers to extract and analyze pristine rock samples from the precise geological moment of the impact and the periods directly before and after. These precious samples provide crucial high-resolution information about the environmental conditions that prevailed before, during, and in the immediate aftermath of the catastrophe. Paleontologists contribute immensely by discovering and meticulously studying new and existing fossil remains, helping to build an ever more detailed and nuanced picture of the specific species that vanished and those remarkably resilient ones that managed to survive. This foundational work is significantly enhanced by sophisticated dating methods and precise chemical analysis, which collectively reveal the exact age and the chemical composition of fossils and their surrounding sediments, with increasing precision, allowing for fine-tuned chronological mapping of events. Computer modeling has emerged as an invaluable and indispensable tool in reconstructing the complex and chaotic events of the extinction. Scientists now utilize powerful computer simulations to rigorously test various hypotheses about the impact's far-reaching effects. These models simulate global climate changes, the spread of immense wildfires, the generation and propagation of devastating tsunamis, and the long-term atmospheric effects of ejected dust and aerosols. These sophisticated models are constantly refined as new data becomes available, allowing researchers to better understand the incredibly complex chain of events that culminated in the mass extinction. Crucially, collaboration across diverse scientific disciplines is key to advancing our collective knowledge. Geologists who study Earth's structure, biologists who understand life's processes, climatologists who model ancient weather, and astrophysicists who study celestial mechanics, all work together. They share their unique insights and specialized methodologies, creating a synergistic approach. This cross-pollination of ideas frequently leads to entirely new hypotheses and innovative approaches to testing them, gradually, painstakingly, building a more comprehensive, accurate, and truly holistic picture of one of the most significant and profound events in Earth's entire history, an event that reshaped the very course of life. Dinosaur fossils, those incredible geological treasures, manifest in several utterly fascinating and distinct forms, each offering its own unique and invaluable insights into the vanished world of prehistoric life. Bones and teeth are without question the most common and immediately recognizable fossils, often forming the iconic centerpieces of museum exhibits. These hardened remains, durable enough to withstand the immense pressures of geological time, provide absolutely crucial information about a dinosaur's sheer size, its intricate skeletal structure, and perhaps most tellingly, its specific diet, the very essence of its ecological role. Paleontologists, armed with their vast comparative knowledge, can often identify specific species, or at least a genus, from a single distinctive bone, or even a solitary, uniquely shaped tooth. The subtle ridges, grooves, and attachment points on these ancient bones speak volumes about the musculature and soft tissues that once encased them. Trace fossils represent another immensely important and often overlooked category of fossilized evidence. Unlike body fossils, which are the remains of the organism itself, trace fossils are the preserved indicators of a dinosaur's activity. This broad category includes the unmistakable impressions of footprints, revealing moments of ancient locomotion, extensive trackways which are long sequences of these footprints, chronicling a journey, and even the remarkable and sometimes surprisingly insightful coprolites which are quite literally fossilized dung. These remarkably preserved vestiges of dinosaur activity offer invaluable clues about their complex behaviors, their specific movement patterns, and even surprisingly detailed aspects of their dietary habits, what they consumed and how they processed it. The ripple marks left by a wading dinosaur, the drag marks of a tail, the scratchings on an ancient log, all are trace fossils, each a silent story from deep time. The discovery of fossilized dinosaur eggs and nests has also proven to be profoundly enlightening, sometimes even containing the incredibly rare and delicate remains of embryos still nestled inside. These precious finds have revolutionized our understanding of dinosaur reproduction, their nesting behaviors, and the intricate process of their embryonic growth and development. They reveal whether parents cared for their young, how many eggs were laid, and the structure of ancient nurseries. Even rarer but incredibly informative are skin impressions and feather imprints. These delicate and ephemeral traces, preserved only under exceptionally precise conditions, provide direct and undeniable evidence of a dinosaur's external appearance, revealing the texture of their hide or the presence of plumage. Such discoveries have profoundly revolutionized our understanding of their aesthetic qualities, and perhaps most significantly, their evolutionary relationship to modern birds. In some truly